Can somebody hear me, see me?
Yes, Girish, we can see you and we can hear you.
Okay, great. So I'm going to see if I can run that PPT on this laptop. Can somebody hear me, see me?
Yes, Girish, we can see you and we can hear you.
Okay, great. So I'm going to see if I can. Good afternoon.
No, the narration is not audible.
Hi everyone, can you hear me? I cannot hear anybody.
Yes, we can hear you.
Yes, okay. I got an ad. Thanks. And could you also see my screen just a few seconds back?
Yes, I was able to see your screen at least.
No, I'm not.
No, I unshared it. I just wanted to check. Okay.
Hello, am I audible? Just checking. This is Anup Krishnan here.
Yeah, Om Damani here from
Yeah.
Bombay.
Yeah, we can hear you. I have made you a co-host, so you can share the screen. Share
Oh.
your screen. Yeah.
Epidemiology in particular and mathematical biology in general.
Yeah, Girish, we can hear you. It's a bit scraggy, but we can hear you.
So Jasjeet, can we start or should we wait a little more?
I think we should start because let me just make sure that the speakers are mostly in. They are. So, all right, welcome everyone. This is Jasjeet Bagla from ISA Mohali, and we are happy to host the first online symposium from ISRC. This one is on modeling for COVID-19 in the Indian context. I'll pass on the mic to Pinaki, who will take. No, I think I pass on to Jam and then on to Pinaki. Jam, are you here?
Yes, thank you, Jasjeet. I'll just speak a couple of words about ISRC before we start. This is the Indian Scientists' Response to COVID-19 group. It came together towards the end of March as a voluntary group of, started off with very few people, and many people from various institutions, from various disciplines and universities joined, and it has grown to be a large group with about 600 members actually right now. We have working groups on different topics, and people break into groups and work. One of them is modeling, and this is the group that is organizing this meeting. We have another group called Hoaxbusters, which has been looking at fake news in the media and debunking it, producing resources. Then we have a group on science communication, which tries to produce material, especially for people in very low resource conditions and for different target audience. We have a group otherwise also looking at different material and media. We have a group looking at hardware, and we are active on social media. So please visit the ISRC website, which we'll put up in chat, and welcome you all to this meeting. Thank you. Over to Pinaki.
Yeah, so good afternoon and welcome to this first event in the series of symposia that we plan to have. So the idea is that we'll have most of the groups which are working on modeling how epidemic is spreading in the country to come together and give their presentation on how they are looking at modeling. So there's a wide range of groups that are working throughout the country, and the plan was to bring some set of them together today. So we will hear a wide variety of modeling that is being done from different perspectives, and we have a great bunch of speakers to talk about that. So I'll introduce the speakers, but before that, I'll just remind the speakers that it's about, everybody has 20 minutes, so roughly 15 minutes for presentation and 5 minutes for questions. So after each presentation, there'll be a Q&A, and the questions I request the audience to post on the chat box. So we'll pick up some of the questions from there, and then the presenter can respond to that. So after we finish all the presentations, there will be a brief panel discussion. And so the speakers can exchange their views on how to go forward, specific questions to look at. And we'll also take a few questions from the audience, again, via the chat box. And if you have any extensive thoughts to share, please send us private message, either to me or Jasjeet, and then we'll take it up from there. So the speakers for today are Mukund Thattai from NCBS Bangalore, N. Anup Krishnan from IIT Delhi, Gautam Menon from Ashok University, Sonpat, and also at IMSC Chennai, Om Damani from IIT Bombay, Sai Vignananpati from IIT Bombay, Girish Setlu from IIT Guwahati, and Rajesh Sundararasan from ISC Bangalore, Harshal Hadnagarkar from ThoughtWorks Pune. So from wide variety of speakers and from different parts of the country, hopefully we'll have a wonderful discussion. So I request Mukund to kick off proceedings, and he'll be talking about spread of COVID-19 in India at successive geographical scales. Over to you, Mukund.
Thank you very much, Pinaki. Thank you, Jem. And thank you, first of all, for inviting me to speak at the symposium. I think it's very important that we're able to share the work that we're doing so rapidly and with large numbers of people through this platform that's been built over just very few weeks. First of all, I just want to check if people can see my slides.
Yes, we can.
Okay, great. So I'll get started. So what my role here is, what I've been trying to do is not to make predictions about where this pandemic is going, but I think it's very important for us to understand what we are going through right now. In other words, to look back and see whether the patterns that have already occurred, given the data that are available, match what we expect from our basic understanding of how diseases spread. So I'm going to be speaking in particular about the spread of COVID-19 in India across multiple geographic scales, starting at the level of the individual and going up all the way to the level of the country. So to begin with, of course, the infection arrived in India from abroad, and the first set of cases that were known because of the way the testing criteria were determined were all international travelers or their primary contacts. And these were contact tracing was carried out by local authorities throughout the country. And over the period from the beginning of March to the very end of March, up till March 31st, there was a total of about 500 international travelers who tested positive and whose contacts were traced. About 462 of them did not cause any known infection, and the rest caused infections according to this little graph that I showed. So each red point is an international traveler, each gray point is a local contact who was infected. You can actually use this graph to plot the probability that a given infected person infects a certain number of secondary cases. That's the histogram shown on the right. And this histogram is well fit by a negative binomial distribution, which is a standard type of distribution to account for the idea of super spreading. So what is super spreading? So if you assume that the basic reproduction number is 2.5, then given the negative binomial fit to the contact data, you expect about 80%, 78% of infected people not to cause any further infection. On the other hand, about 10% will seed 7 or more infections. And these are called super spreading events because it's much more than you expect from a sort of homogeneous Poisson distribution type of assumption of how infections spread. Going to a slightly higher scale now, or all the way. So by March 31st, we know and have traced a certain number of international travelers and their contacts. And if you just mark the total number of international cases known in every state on March 31st, which remember is a few days after the lockdown, but cases have a lag of coming in. So I assume this still reflects pre-lockdown dynamics. And if you plot that in the left graph against all cases on March 31st, which is in dark blue, or on April 26th, which is in orange, you see that on March 31st, there's a very tight correlation, which means that basically it's the imported cases that are driving the epidemics locally. But by April 26th, there's a huge amount of divergence between states. I've shown similar data on the right, except now it's the number of districts that had international cases on March 31st, and the total number of cases by April 26th. And you can see that there are basically two kinds of things. One is a set of states that don't have an epidemic now, and the other is a set of states that do. There is a correlation with imported cases, but remember, this is just a correlation. It's very likely that large states will have many more imported cases simply because they have more international travel and so on. So this is not meant to be a causal statement. But I will say that the number of imported cases on March 31st is a very good summary of future predictions of infection, at least up to some point before the states diverge. So then my goal was to understand, why did the states diverge in their dynamics? Why did some states like Karnataka and Kerala go up by just a few factors from their very high caseload? In fact, Karnataka and Kerala and Bombay in particular were the highest number of cases on March 31st. And yet now they are in the bottom half of all states, whereas states like Maharashtra, Gujarat, Rajasthan zoomed up from a very low starting point. So to understand this, we need a model. And I'm going to present my modeling framework here, and I'm happy to take discussions offline or later about how this works. But very, very quickly, you can write down the total number of infections, I of t, in the following integral type of equation. It depends on the number of initial infections, depends on the rate of new infections, which is the product of the number of sensitive people S, the current number of infected people I, a prefactor beta, and a so-called infection kernel, which says the probability of somebody infecting somebody else at time t, given that they were infected themselves at time t prime. This fairly complicated way of writing things actually reduces right down to the basic SIR model, whose differential equation I've shown on the bottom, if you assume that this infection kernel phi is of the simple exponential form e to the minus alpha t. So what I've shown as this big complicated integral equation on top is actually just the SIR model if you take phi as e to the minus alpha t. However, if you want to include more details, for example, like the SEIR model, which accounts for a certain amount of infection after exposure before symptoms and so on, you can actually modify phi to take into account all this data. Here I've shown an example where phi has a sort of Gaussian shape, which is peaking at around 5 days. So I'm going to use for the rest of this talk the infection kernel shown over here, which was reported in Science from contact tracing data. And it basically says that the peak of probability that someone infects somebody else is happening at around 5 days, with a standard deviation of about 2 days and a fairly reasonable Gaussian shape. By about 2 weeks after infection, the transmission probability is assumed to be low. So that's the infection kernel, and that's why it's useful to write down the model in terms of infection kernel, because you can account for all these details of viral dynamics. But there's another useful reason, and I want to go over that in detail here. This is the whole model. So we want to model spread in a country of 1 billion people, but we want to start with a single individual. The only way to do this is a hierarchical model, right? So I'm going to assume a sort of scale unit of 2 to the 5, 32, or about 30. So I'm going to assume that individuals have a social group of about 30. About 30 groups make a locality of about 1,000. Localities make wards of about 30,000. Wards make districts of 1 million. States of 30 million, reaching up to a country of 1 billion. And we're going to try and model the spread across all these levels. And the way we're going to do this is, in fact, drawn from the mathematics. Just as two patients, one individual can infect another through some infectivity kernel, one group can infect another through contacts by relative individuals, but the infectivity kernel of the group is slightly different. In the same way, one district can infect another through contacts by individuals between those districts. And what I've shown in this little graph here is the calculated infectivity kernel going up and up and up across geographic scales. So what you see is basically that the process slows down at higher geographic scales, and the peak of infectivity actually drops, not too much, but drops below what you would expect at the level of an individual because of the way the disease decorrelates across a group. To be specific, the kernels are actually calculated from the equation I told you earlier. The kernel at level K is the infection number at level K-1, and I'm happy to discuss this further. The model essentially has only 3 parameters. One is not even a parameter, it's the scale of the units, which I'm saying is about 30, 32. The other parameter is the basic contact rate, beta, which is part of the standard SIR model, for example, the bare contact rate. The final parameter is very important. It says the probability that my contacts are clustered within my social group or in my neighborhood, locality, ward, district, state, and so on. And I'm assuming that's going to take an exponential or a geometric type of profile. So I have successively fewer contacts at larger and larger geographic scales. And I'm going to assume a value of 0.1 for that reduction. And that lambda is basically the only free parameter of the model. And the reason is because the beta, the contact rate, is chosen so that the basic reproduction number R0 comes to 2.5, which is a sort of standard agreed upon amount for COVID. So you can actually use this model and you can use it to predict when a starting infection from one individual, after how many days will it first hit another ward that the individual is not in, or another district the individual is not in, or another state the individual is not in. And that's plotted on the left here. So you'll see that obviously the wards get hit early in the same state, in the same district, and then districts in the same state, and then to other states. And there is a spread. Again, a very important point that the infection slows down as you have to reach successive scales. And there's a very interesting sort of 2-wave pattern at the level of districts and states, which is not apparent at the level of very local geography of a ward. The total infections in each geographic zone, because of the way the model is set up, of course, will reach a fraction which is consistent with R0, basically 1 minus 1 over R0. Okay, so I'm going to spend the remaining 6 minutes discussing how this model actually matches with data. I'll just remind you, it has basically one free parameter, which is this assumption of how contacts decrease at successive geographical scales. The other parameter, 2.5 for R0, is chosen from data, and the infectivity kernel of a given patient is chosen from data. Right, so this is not a fit that I'm showing. First, I want to show you the data. So you can actually obtain this data from the COVID-19 tracker project, which I cited in my first slide. So you can get day-by-day district-wise tallies for new cases and similarly state by state. What I've shown you here is for 12 states, which have the largest infection so far. In gold color is the cumulative number of infections for the state. And in light and dark blue are infections total in early and late districts. I haven't put the names of the districts here, but I can tell you what they are if somebody's interested. The pattern that you see is that you see early districts rise, then with some delay, you see late districts. And that delay is reflected in the total number of infections at the state level as well, because you see this kink in the growth rate of that state at the time when the late districts take over. The pattern is slightly different when the first district that gets hit is one of the largest districts, right? So that's the case, for example, in Tamil Nadu or Karnataka, which is Chennai and Bangalore. But it is especially visible when the first district is small and the later districts are large. You see this crossover event and a sort of sigmoidal shape for the total number of infections in the state. The same pattern, because of the hierarchical nature of the interaction, should be visible at the national scale as well. So I've plotted the data over here. In dark brown is the total cumulative cases in India for the dates shown. In gold, the cases for Maharashtra, and then for the 2 early and late districts in Maharashtra, which are Pune and Mumbai. Late is, of course, a relative term. There are still many districts that are much later in the course of the infection. So what you see here is that the kinks that are visible in the Maharashtra trajectory are also visible at some level in the India trajectory. And again, that's because there are early states like Haryana or Kerala, and then there are late states like Gujarat. On the right, I've shown the model whose only free parameter I've chosen as 0.1 just to be reasonable. It's not a fit. And you can see a rather remarkable agreement qualitatively in the countrywide progression here. Okay, it's not an exponential growth curve. It's not even a straight line. The countrywide growth curve shows these oscillating patterns that reflect the first arrival in a ward, a district, a state, a country. And I hope you can see that the national data do match that kind of oscillating pattern. To re-emphasize the point, I want to show you here not the cumulative, but actually number of cases per day, the rate of increase. And I've shown it on the left for days since March 1st, and I've shown it for India in dark brown and for Maharashtra in orange. And on the right, the same model, the same parameters, it's not a fit. You can see that the state-wise orange pattern, there's a kink for early days, and then there's going to be an upswing, which is not yet visible in the Maharashtra chart, and that's for later districts of Maharashtra. But in the country, there's a kink, and then there is an upswing, which corresponds to later states of the country joining the wave. And again, you see a rather remarkable qualitative agreement in the patterns of these curves. I want to point out right now, this model is not a fit. It's not a prediction either. You should not take the numbers of the model seriously. You can already see that the numbers in the model are an order of magnitude or more off from the numbers in the data. And this is a question about why there is a discrepancy. I haven't modeled the lockdown, and that's part of the reason. Could also be lack of data. But the numbers should not be meaningfully compared. That's not my goal here. What you should take away from this message is the idea of early districts and states, and then late districts and states, and a characteristic wave, which seems to be indeed visible in the real data. Okay, so I'm going to end now so that there's enough time for questions with some open questions. First of all, I haven't modeled the lockdown. My goal was just to see, what is the null model, taking what is known about biology of the virus and seeing how it fits into a hierarchical setting in India. Okay, so it's not a fit to the data, and how to put the lockdown into this framework to explain the discrepancy of the two numbers is something that will need to be worked out. The second thing, which is very interesting to me, if you try and bring the total numbers down to match the data, it also slows down the spread. In other words, the time scale and the total amounts are related. And it's actually difficult to find mechanisms that control just one versus the other. So there is something interesting going on in the real data, which is not accounted for in a simple one parameter model, obviously. And so the model will need to be made more complicated to account for lockdown. The final word is that absolutely the most important thing here is that lambda drop-off rate as a function of geographic scale. How many contacts do I have in my group, in my locality, in my ward, in my district, in my state, right? For most people, most contacts are within groups and localities like employers, and fewer, exponentially fewer contacts going out. But that drop-off is what's controlling the dynamics as you see here. And therefore, things like inter-district and interstate travel will be expected to have a very large impact. So I've reached my 15 minutes. I'll stop over here. Just want to acknowledge we have a very interesting and dynamic modeling group operating within TIFR with a lot of my colleagues who've already put together a lot of studies and preprints on this. And I'm amazed to see how fast the science is going and how fast we're able to share, exchange, and critique our data. At my own institution, NCBS, thanks to Sandeep and Madan for inputs, and to Dilawar for helping me with the data. Again, for discussions, JNC SR Srikant Shastri, and early discussions and a lot of just basic conversation with Gautam has been very useful in helping me learn about how to do all this. So I'll stop there and I'll take questions. Thank you.
So thanks a lot for being on time. So a couple of questions to begin with from Carl Brito. So is population density a parameter in these models? And also rates of testing increased with time. Could you explain some of the kinks? Could that explain some of the kinks that you mentioned?
Yeah, so remember, I'm not trying to explain the data. I'm just taking a very simple model, making a prediction, see how it fits with data. This being keeping with the philosophy of a null hypothesis. The goal is not to add so much detail as to be able to explain all the kinks. And the summary is that you can get the kinks with no further input. Population density, it's absolutely arising effectively in the model. What the model has are numbers, right? But the fact that the interactions are higher within your local group and slightly lower in your locality and so on and so forth, that captures some idea of local population interactions. If the question is about heterogeneity in density between different regions, that heterogeneity is not in the model. It assumes a uniform type of self-similarity at all nodes and at all levels.
Yeah, I think this is also related to the next question from Mithun, which he asks that if I understand correctly, the infection kernel is obtained by fitting to data at the appropriate level. Is this done for each district or each state individually, or is there some average kernel at a given level?
Again, the infection kernel is not done by fitting. What you do to in my talk, there are two separate threads. One is the data and one is the model, and the model is not fit to data. The infection kernel starts off with one patient's infection kernel. You put that into the model, into the integral equation that I showed you to find out how many infected people I get in a locality. You put that back in to get how many infected people you get in the district, and so on. Those calculations are how you get the infection kernel. I don't fit to the data at any point. I just have one free parameter, which is lambda.
So the next question is from Chandran Venkateshwaran. Looks like that the late districts show more cases eventually than the early districts. Any idea why? Or is it just a coincidence?
Okay, so here when I showed you the graph of late districts, okay, here on the right, it's the sum of all the late districts, okay? So it's one early district plus the remainder, and the sum of those two should match the whole state in the model. Now, if you look at the data, the patterns are slightly different for states where the early districts were small and the late districts were large, or for states, for example, like Tamil Nadu or Karnataka, where the first districts are large. Okay, so by just looking at the variation in the district size, you should be able to reconcile what the patterns look like over here. It's not that the late districts cause more cases. Eventually, all districts reach the same saturation number, which is 1 minus 1 over R, because that's the so-called herd immunity threshold. It's the fact that there's only one early district, but many late districts waiting in the wings that causes the crossover.
So some people are asking about the definition of early and late districts. It's just when the infection is hitting each district, right?
It's when the infection hits each district. Very strictly, early is the first district, and late are all the others. And when the infection reaches all the others is given by this graph on the left. If it hits the first district on day 0, then the other districts, which are all counted as late, started around 25 days.
So we'll take last couple of questions. So from Vijay Jindal, we always talk about number of infected persons. My question is there a parameter to identify severity factor leading to mortality link?
Okay, so of course, I'm not going to model mortality and so on. It's not that type of detailed model, but there are other people in the symposium who will bring that up. And so maybe we can wait for that question to be taken by later speakers.
So one more question maybe. So from Ajay Thakur, is there discrepancy in numbers between data and model due to 1 in n cases actually being reported, lockdown helping damn the number of infected, and a combination of both A and B?
Could be all of the above. It could also be that the model is exceedingly simple, and therefore we should not expect such a simple model to give detailed number agreement, only qualitative agreement.
Thanks, Mukund. I think we should move on to the next speaker. So we'll come back to the discussion on your talk later again. So next speaker is N. Anup Krishnan from IIT Delhi. So Anup, you can start.
Yep. Can you see my screen?
Yeah.
Okay. Let me see how to go full screen. Okay. Can you see my screen now?
Yes.
Perfect. Great. Thank you. Thank you for giving me an opportunity to present our work, Prakriti. The title of today's presentation is Prakriti, a highly granular model for COVID-19 for effective planning of control strategies. So for those who are thinking what Prakriti is an acronym that we have come up with for prediction and assessment of corona infections and transmissions in India. So we have a web page also, and I'll be discussing about this in detail. This work is done by a group of PhD scholars and undergraduates and a few volunteers, Ravinder Hargun, Saurabh, Suresh, Amreen, mostly working with me and in collaboration with Professor Hariprasad Kodamana of Chemical Engineering, IIT Delhi, and Professor Amit Sharma of ICGB, New Delhi. Great. Can you see my screen?
Yes.
Yes, we can. We have all muted our mics, so don't worry about
sure.
sound.
Sure, yeah. Okay, so I'll try to present it this way because sometimes it's getting stuck when I'm pressing next with the full screen mode. So here we are together for to discuss about COVID-19 and some of the major issues the world is facing right now. So you can see that most of the world is already infected by COVID-19. So the major issues that the world is trying to address is one, estimating the nature of spread. There have been a lot of work on that. You saw an earlier model, a wonderful one by Professor Mukund Tattai, and I'm sure we are going to see a few more. Second question is about control and mitigation strategies. So how to essentially balance between the burden on the economy versus the burden on the healthcare system. And the third one is when you're planning any strategies for intervention, either at the local level or national level, what is the common metric that you can look for? So, I mean, there are many metrics that people are looking at. It's just number of infected cases, number of active cases, number of deaths, and many other cases, metrics also, but no commonly agreed metric for this. And then another issue is about resource allocation. So where should you allocate the resources to, hospitals, PPEs, and even other food and essentially resource allocation is also a major issue. So to address this, some of the common approaches that's taken right now is nationwide lockdown. Most of the countries have gone into nationwide lockdown. It's very effective in most of the countries, but it's not scalable in long term, as we can see in India also right now. Another one is a localized lockdown. That means you can locally lock down a few regions, but the problem in this case is you have a large number of possibilities to decide from, and how to go with which option is always a question. Great. So the goal of this work is to combine physics-based modeling with real-time data to enable development of some optimized intervention strategies, or at least to give some directions in those, at least to shed some light in those directions. Great. So let's look at COVID modeling now. And you can see there have been quite a few publications on this. And one of the most commonly used approach is SCIR based model. So I would like to just give a brief idea about this. So you can basically model this COVID either using a physics based model or a data driven model. So a data driven model is purely relying on data and or not anything else. So machine learning based models or probabilistic models and regression based models can be examples of data driven models. But a more common one is physics based model. So that is SCIR based model or SIR based model, and several versions of those. Or if you want to model it at a slightly more granular scale, agent based models or something that you can look for. But some of the major issues that the models, these models present are models in many occasions do not consider the granularity in terms of spread. So if you do not consider the granularity in terms of spread, that may lead to significant overestimation. I'll discuss about that a little later. Another one is the spatio-temporal variations in basic reproduction number are not. So Mukund gave a very, very nice presentation earlier about SIR model and brief idea about what is the mathematical equations behind this. But one of the common approaches that people always use is to keep a constant R0, a basic reproduction number. And here what we will show in next few slides is that the basic reproduction number R0 is going to play a very key role in modeling this the transmission. And specifically, this R0 exhibits a significant large spatio-temporal variations, even in countries like Italy, which are significantly smaller than India. So to this extent, what we propose is we propose an adaptive interacting cluster-based SCIR model. We call it AICSAR AXR model for predicting the granular transmission of COVID-19 in India. Okay, so this is the basic idea of an SCIR model. So you saw these equations earlier in the SCIR model case. So here you just have an additional E coming into this that is exposed. So the basic idea is you take a population, you divide it into 4 groups. First, you divide it into susceptible, that's those people who are susceptible to infection. And then you have exposed, the ones that are exposed to infected people or at least exposed to the virus. And then this exposed get converted to infected, and the infected finally get converted to removed. So it could be recovered or it could be deceased. Great. So this is the basic idea of an SEIR model. But what we specifically did in our AIC SEIR model, that is adaptive interacting cluster based SEIR model, is that we took the total population of the country, and then we divided this total population into subpopulations. So how did we divide it? So you can see a map of India here, and then different states which are part of the country. So what we did is we took these states, we took these geopolitical divisions and divided the total population into each of these subpopulations. Now what we did is that once we have these subpopulations, we applied an SEIR model within each subpopulation. So there are a few tricks in this which I'll be explaining in detail in the next few slides. It's not the regular SEIR model, but slightly modified version of it. And within each state, what you do is you divide this subpopulation as natives and people who are from another state or migrants. So this is a little bit tricky. So the point of this is to ensure that infected people from one place move to another place. The idea is as follows, that let me, so for example, I am right now staying in Delhi, but let's say I'm from some other state, okay? And during this infection, I decide to travel from Delhi to my state. So I could be part of any of the four. I could be part of S, E, I, or R. But I decide to move from my state to my, from the state that I'm currently residing to my home state. And if I belong to either E or I, there is a high chance that I take the infection along with me and then initiate the infection in the new state that I'm going to, which is my home state. So that part is accounted in this model by dividing the total population into natives and migrants. So in our present case, what we did is that we looked into the census data from last 10 years. And what we found out is that on an average, 10 to 15% of population in any state is a migrant population. So we assumed 10% of the total population of a state to be migrant, and we assumed the rest of them to be natives. Now in this migrant also, what we did is that we assigned a probability for each state and distributed it to those states. So this probability was taken basically considering a lot of factors. For example, what we did is we took the total population of a state, we took the distance between the capitals of the state. So the assumption is that if I'm basically from UP, I'm more probable to go to states closer to me than to go to a state that is further to me. So this distribution of migrants is considered to be totally proportional to inversely proportional to distance, directly proportional to the number of metropolitan cities, directly proportional to the population of the state, and directly proportional to the number of tourists visiting a particular. All this data is taken from the census for last 10 years for Indian scenario. And then how do we have this interpopulation interaction? So we have migration, that is people leaving for hometown, or you have people coming to hometown. Okay, so for example, if I'm in Delhi population, I can leave Delhi and somebody else can come into Delhi also. So this is where it becomes slightly different from the SEIR model, because SEIR model traditionally assumes a close population. Here I'm saying it's not a close population, but people can freely move, and irrespective of which state they are in, that is in S, E, I, or R. Great. So this is about migration. Now border control. We add an additional term to account for border control, which is in addition to this migration term. So this migration term tells me which state I am probable to go to if I am allowed to move. Now the border control tells me if I can move or not. So this is again another parameter that we can play around with according to different conditions of the government. So let us say if you have a strict lockdown, then you have C equal to 0. And then if the borders are completely free, then you have 100% traffic, just normal traffic going between the boundaries. So this is how the population clusters are interacting with each other. And then you have an intra-population interaction. That means within the subpopulation, how are they interacting? To that, we did not assume a constant R0, but we computed the R0 for each of the districts, so for each of the subpopulation, that is in this case states, by fitting the incidence data with the SEIR model. So what we did essentially is that initially we took SIR model, but then we understood that if you take SIR model, there is a slight issue because exposed is a major part of this population, and that actually decides the nature of the curve. Because it's exponential, it may start like this, but if you allow for SEIR model, it can even go like this. So this we realized it over time. So what we did is that we took the SEIR model and fitted the data R0 to it, fitted the curve to it in a least square sense and doing all the regular curve fitting methods, and then computed the R0 value for each of the subpopulations. So I was always told that every equation you have in the slide takes n number of people away from the slide. So I'm just not going to discuss this slide in detail. I just wanted to show it to you because this is the SEIR model, and this is the district-wise or state-wise implementation of the SEIR model. It's the same equation, just that now you have it for each district. Okay. So XII, XIJ, YII, YIJ, WII, IJ, NII, NIJ. And these are corresponding to the interaction within the district and with the other districts or states, for example. Okay, so this is the equation that we have implemented. So for completion's sake, I'm just showing it. Okay, great. So we have a very nice model, and I'm saying it is going to work well and all that. So did we try it? Of course, we tried it. Specifically, we tried it in 3 countries. We took Italy, we took US, and we took India. So here you can see how the SEIR model is fitting to R0. So you can see the R square value is almost 1 because the curve is almost going on top of it. And what we see is that the R0 in this case, this is for state Gujarat. If you can see on the left, this is for state Gujarat, and the R0 value is coming out to be 1.71. Great. So we did this for Italy, India, and US, and this is the distribution of R0 values in Italy, USA, and India, each during different time periods. So let me just explain it. The Italy from February 24th to March 1st week, that's when they had the initial cases. US from March 4th to 2 weeks forward from March 4th, and India from March 19th 2 weeks forward. Okay, so this is the first few weeks of heavy infection. And what you can see that the R0 values of India is significantly lower in comparison to the R0 values of Italy and USA. And you can see, I mean, of course, we are fitting it only for 1 week, so there could be some spurious fits. But you can see that overall the R0 value of Italy is significantly high in March 9th. Okay, and then you go forward, 24th of March, it's significantly decreased. The color scheme is here, it's going from 1 to 10. And then once you go 1 more week, 5th April, it significantly decreased and most values were close to 1. And in US, you can again see the same thing that, in 18th March, only very few states were affected. So the gray ones correspond to the states where we have not computed R0. And then when you go to the 5th of April, you can see that the states are significantly affected and different values of R0. And this was the case for 4th April in India. Some of the states are not significantly affected, so they're not included. So what is the main message out of this? A constant value of R0 cannot be used either spatially or temporally. Okay, so with this, what we did is that we extracted these values of R0 and then put them into our AIC SEIR model and then predicted the trajectory for different states in different countries. So here you can see we did it for Calabria in Italy, Idaho in USA, Madhya Pradesh in India, Veneto in Italy, Washington in UP, and Washington in USA, and Uttar Pradesh in India. So interestingly, what you see is that even for districts which had no initial cases, that is what I0 equal to 0 means. So these states had basically no infections in the beginning, and still our model is predicting pretty well for these districts, these states as well. Similarly, for Idaho and Madhya Pradesh, you can see these are all 3 states which had no infection. So in order for infection to start in this state, it should move from one state where there is infection through our AIC-SEIR model, reach an initial infection there, and then start spreading it according to the transmission dynamics there. And similarly for other states which had sizable number of initial population also, our model is predicting it reasonably well. Great. So now we move on to a comparison between SEIR model and our AIC-SEIR model. So you can see if you have a single cluster SEIR model for the entire country, it significantly overestimates both the peak and the time at which the peak occurs. So here the dotted line corresponds to the AIC-SEIR XR model, and the blue line corresponds to the single cluster model. And you can see we have simulated it for different values of C. C equal to 1 means completely free traffic. C equal to 0.5 means absolutely, reduced traffic, basically 50% of the traffic. And 0.1 means only 10% of the traffic. Of course, we did not simulate it for C equal to 0 because we felt it to be a really unrealistic scenario. So this suggests that basically the XR model predicts the peak to be significantly lower, and extending this further, what it suggests is that if you have a lower, much more granular model, the peak will be much more diminished and more spread. Okay, so
Anup, just a reminder that you have only 3-4 minutes left for your 20 minutes.
Perfect. Yeah, I'll be finishing in 3-4 minutes. Thank you. So this is our granular R0 in India. What we did is that we just took the same thing and then computed the R0 in 30 states in India. So you can see the R0 varies from 0.07 to 3.38 if you consider the state-wise model. And then for 730, sorry, it's not states, it's districts. Please read it as districts. So for 730 districts in India. So you can see the R0 is mostly not calculated for many districts because they have few cases. So even in this case, you can see that the R0 is varying from 0.03 to 5.45. Then this is the histogram of the R0 values for different weeks. Week 1, 2, 3, 4, 5, where 5th week is the last week of April. Okay, so we're starting from the last week of March to last week of April. So you can see how the R0 is varying from states and the district-wise cases. And specifically, if you look at the mean R0, you can see this is the mean R0. So if you look at the district-wise model, you can see that this is continuously decreasing, and this can be completely attributed to lockdown. So you see we start from 5.5 value and then we go all the way down to 1. And while if you look at the states, then you see slight increase and then decrease. So this also suggests the reason for using a more granular model instead of a model like this. Based on this, we developed a dashboard called Prakriti. So it's a web-based dashboard, and it provides detailed state-wise and district-wise predictions of COVID-19. It provides the basic reproduction number at a very granular level. So you can all go to the website. The website is prakriti.iitd.ac.in. You can all go to the website. I'll show it after the presentation. And then look at the R0 values currently in each of the states and districts. So if you have any comments or suggestions, please let us know. We'll be glad to make any changes to this accordingly. And this is really tailored for Indian scenario. We have 730 districts models, and the predictions are given for a 3-week period. So we are not predicting it for the entire curve because it doesn't make sense to predict it for the entire curve, but we are doing it for a 3-week period, and every week we are updating it. So our next update is going to come tomorrow, that is May 10th. We'll be updating the data, and like this, we will be updating it every week, and the projections will be for 3 weeks forward. And you can extract the R0 value, the district-wise cases, state-level cases, and the country-level cases. And we strongly believe this enables authorities and public to plan intervention strategies and resource allocation. So the main conclusions: R0 exhibits significant spatiotemporal variations, which needs to be accounted in models. And the XR model presented here can provide a very granular trajectory of COVID-19 in India and potentially the rest of the world. And finally, the XR model allows the simulation of various intervention strategies at granular level, thereby allowing this policymakers to make an optimal choice, balancing the long-term socioeconomic burden and short-term healthcare burden. Some things required for future work. What are the data required? We really need accurate district level data of testing and the number of cases. And some of the model limitations is, as I said, we can predict it for short term in reasonably well, but long term is not possible. And it's not able to account for untested cases. And that's why we need the testing data to basically add a parameter that can account for this. Some of the future work, we believe this model presented here is very generic and can be applied to other countries as well, and other infectious diseases as well. And there are many parameters that we have not included, which is something like, for example, population demography, that is age and sex, exact data on migrant workers, seasonal variations of R0, etc. So before concluding, I would like to thank my collaborators and students who worked on this. I must say that Ravinder, one of the PhD students working with me, did most of the work on this. I'm just presenting his work. It's really his hard work that you're seeing. And of course, Hargun Singh, who developed the web page and the interface and everything. The whole thing was done in a week's time. So they really put in a lot of sleepless nights. And of course, I need to thank my collaborators, Professor Hariprasad Kodamana and Professor Amit Sharma from ICGEB, who gave really, really nice inputs on modeling. With this, I would like to conclude my presentation, and I'm just taking it to the web page.
So thanks, Anup, because we are running out of time. So I'll just shoot off a couple of questions that have come in. So one question is basically, so how many free parameters do you have in the model? And so that is one question. And another question maybe you can answer is also, so in R0 estimates, how much, whether you have computed uncertainties and so on. So these two questions.
Yeah. So right. So this has been extensively done, and we have already written a paper on it. So this is under review. So if you go to this, you can see the R0 values and the estimates in uncertainty, and the goodness of fit is also given, the R square values for most of the states. So if you have low number of cases, then you will see that the goodness of fit is very bad. So in those cases, we took the country average, the state average as the case for that district. But if we have a lot of cases, then the R square fit is really good, and the uncertainty associated with this is very low. I have the entire, for all 730 districts, we have the curve for it, so I can share it with whoever is interested.
Yeah, and about the free parameters. So how many free parameters do you have?
Yeah, so the number of free parameters is basically R0 is a fitting parameter. That's the main free parameter that we have. And another one is we initiate a matrix. So when you are initiating a matrix, what you're taking is we are taking the population and then we are distributing it. So when you're distributing it, we are assuming that 10% is migrant population. So that these are the two free parameters that we have in our model.
Okay, so thanks a lot, Anup. Maybe we'll come back to your discussion at the later half. So
absolutely, I see that there are lots of chats. I'll go through it and probably be able to give some answer towards the end of this. Thank you.
Thanks a lot. So next presentation is by Gautam Menon. So Gautam, if you are ready, we can start.
Okay.
Is my screen visible?
Yeah.
Okay, fine. All right. There's a bit of a hitch there. Okay, so can I start?
Yep.
Okay, so I want to describe what we call the InSciSym model. And this is work that's been done with the modeling group at InSciCov over the past 2 months, roughly. This work is available on the InSciCov, which is the Indian Scientific Response to COVID-19, the ISRC page. And it's currently in the form of 2 reports, one put out on April 18th, one on May 5th, just a few days ago. And the first one describes the model that I'm going to tell you about now. The second looks at a particular application, which is to the question of what is the best way to emerge from a lockdown situation? What is the best way to relax a lockdown? Accompanying these 2 presentations is also a dashboard, which is the InSciSym dashboard, where you can try many of these things on your own, try a simulation for how, as you impose different types of interventions, for example, a periodic lockdown, a single lockdown, etc. And you include factors like the migration between cities, the migration between states, etc. You can change or vary the answer that you're actually, and as well as the stringency with which you impose any of these constraints. So what we wanted to do in the beginning was to provide a state-of-the-art compartmental model for COVID-19 spread in India in its states and its districts. So that was the sort of dominating theme of what we wanted to do. As part of this, we wanted to look at what might be thought of as benchmark rates for modeling. I mean, models require specifications of rates, and the more complicated the model is, the more rates they take in. Many of these rates relate to biological parameters, and they can be refined further as we know more and more about the patient's sequence through this disease, through the etiology of the disease. We wanted to include demographics, that is state population, and details about migration. In particular, what we wanted to do was be able to evaluate what are called non-pharmaceutical interventions. For example, lockdown, staggered lockdown, periodic lockdown, et cetera, light switch lockdown, and so on, and see which might work best in which particular context. Then we wanted to provide an online tool so that people could actually test all of this out on their own, exactly has been done in the earlier talk as well as to make easy updates possible and changes, whatever we did to the code, we also wanted to make that transparent. So let me describe the difference between the standard SEIR model and the more complex model that we're talking about now. So the SEIR model, as you learned both from Mukund's talk as well as from Anupkrishna's talk, is a susceptible, exposed, infected, and recovered states. What we wanted to replace it by is something a little more that truly is representative of an individual patient's trajectory through the disease. So everyone starts off in an exposed state once you're infected. So you have a susceptible compartment. The moment you're infected, you move into an exposed compartment. And from there, depending upon your age, your predisposition to disease, your other types of conditions that you might have, and so on, you can be either mildly ill, in which case you move from the exposed to a pre-symptomatic category for about 2 days, and then to a mildly ill category for about 5 or 6 more days, and then to a recovered category. If you're severely ill, you move from exposed to a pre-symptomatic category, to a symptomatic category, which is a serious symptomatic category, a severe symptomatic category, and from there to a hospitalized category, and there to recovered. If you're critically ill, you move from the exposed to the pre-symptomatic, to the severe, to the hospitalized, and then you have 2 options, either that you move to a death compartment or a recovered compartment. And in addition to all this, there is the asymptomatic trajectory, which is infected. So you move to the exposed compartment to the asymptomatic compartment, where you can infect other people, and from there to the recovered compartment. And what you have on the x-axis at the bottom of the graph below is the number of days, the progression of the disease through the number of these days. And you can see that the lengths of these compartments roughly reflect what is known from the etiology of the disease itself, of COVID-19. You can translate this. So this is the model that has been appeared in various forms. And the form that we saw it in was the form that Mordecai at Stanford had written it down. You can convert this into the standard compartmental description that people use when they write down equations that describe how people move from compartment to compartment. So the S compartment, the E compartment, so you move from S to E at a rate beta. So that's the fundamental rate in this model, and beta is related to the reproductive ratio that you heard about. From the exposed compartment, you can fork out into either being asymptomatic or pre-symptomatic. From there, you can move from pre-symptomatic, you can move to the mildly symptomatic and then to the recovered state, or you can move to the severely symptomatic, to the hospitalized, and then to the dead state or the recovered state. So all of these arrows between these compartments illustrate specific trajectories through the disease that you can tune based upon the rates that I described a little earlier. There's an addition to the arrows, to the dark arrows with the various Greek symbols involved that tell you how exactly the branching happens and what are the rates at which you move from compartment to compartment. You'll also see a dotted line with the notation CS, CP, CA, and CM. So these reflect the contacts, the effective contacts that take infected people and connect them to susceptible people. This is important because you can choose different interventions that target, for example, the symptomatically infected versus the asymptomatically infected or the pre-symptomatically infected, and vary these CS, CP, CA, and CM independently. And I will tell you exactly how we use these to implement certain types of interventions in the model. So as I said, the Cs represent the intensity of contacts, and tuning these Cs is a non-pharmaceutical intervention because you're just controlling the rate at which people interact with each other. The products of the Cs and the betas together determine R, and that's what sort of makes the situation a little more complicated. Reducing R is equivalent to a lockdown. Reducing Cs you can think of in many ways. If you imagine that you can change Cs with time from being strong in the beginning to weak at the end, that's like a system in which you can immediately test and quarantine people who test positive and remove them from the general population, thereby weakening the link between the infected and the susceptible. So it's really manipulating the betas and the Cs that enable us to look at different interventions in these particular contexts. So the model parameters are described on the top left. Again, it's just a question of detail, and you can get these off the website if you want to look at it. The schema of the model is in the bottom left-hand corner, and the equations themselves are to the bottom right-hand corner. So now you can see that instead of having 4 compartments, which is the SCIR is traditionally written, you now have 9 compartments, and these rates describe the transition between each of these compartments. Each of these compartments can further be subdivided according to age structure. So you can have 0 to 10, 10 to 20, 20 to any number of age compartments you have. You can also generalize these to have at-risk structure as well. For example, some fraction of the population could be at risk because of pre-existing conditions. You could also put that into the model by tuning these parameters appropriately. So this is the meta-population model. So we started off by describing this for states and cities. Now it's a model at the level of districts. It's an age-structured model currently, although some of the results that I will describe will not bother about age structure. We'll just assume that the population is homogeneous. It incorporates migration, the ability to move from state to state. It incorporates healthcare accessibility in its current version, although it isn't there in the earlier set of slides. You can look at the population that is unable to access healthcare or hospital. Connections between the compartments that I described that account for this. Something that we plan to do a little further on is to look at healthcare metrics and look at the quality of healthcare district-wise, with an addition of some health economics input at that point. For cities, we've looked at, again, meta-populations of cities plus migration, the network of 318 cities and how they transfer people from one to the other. If cities are connected, if there is a direct link between these cities, we call them as connected nodes, and we look at migration along these nodes. The migration is balanced, that is, there is no net population change across these different components. So there is no net amount of people leaving Delhi, say, to go to Bombay, but we can change that as time goes along. So what we do in these calculations is make a couple of assumptions. The first is that you have to assume values of exposed, pre-symptomatic, and asymptomatic people in the population. These are hardest to estimate because there is really no way in which we have of actually doing this, unless you have a population in which you manage to test everybody to try and estimate, to try and find out how many are asymptomatic within that. So we choose a range based on the number of positive cases and what we understand from the data that is coming out. We spend some amount of time looking at reproductive ratios, the beta parameter that I told you about. So right now we assume these, we either take them for granted in the sort of spirit that Mukund had used in the beginning, a 2.5 value. We take somewhere between 1.6 and 2.4, depending upon the situation that we're trying to model. Or we can use it in a somewhat more sophisticated way using models such as the epistem model, as well as Bayesian techniques. These are methods 1 and 4 of the Imperial College techniques, toolbox of techniques to estimate the reproductive ratio. This you take in time series for daily incidence and serial interval statistics in order to estimate values for the current reproductive ratio of India. This is not the basic reproductive ratio, but what it is currently at the level of after interventions have taken place. So right now for 6th May, our calculations give you a number of about 1.55 for India, and for Maharashtra 1.54 for 24. And we will use this number a little later to make certain predictions for Maharashtra. So I'm going to use a bunch of different examples. I'll take Maharashtra as an example. Also Tamil Nadu, Chennai, Pune, all as different examples of the sorts of things that we do. We start with a certain number of infected people, exposed people, with a total population of about 11 crores, which is representative of Maharashtra. We have no initial hospitalized, dead or recovered cases. We simulate lockdown by reducing the value of beta to a value of R0, which is less than, which is around 1, maybe a little less or maybe a little more. We think of imposing a lockdown on the 30th day. A single lockdown lasts for 30 days, and then you can impose a sequence of periodic lockdowns for 7 days, a 5-day break, a repeating 7 days, 5-day break, etc. We alter the C parameters we interpret them in terms of quarantining and testing of different people. And you assume that because it's just so hard to identify asymptomatics in the population without identifying them from within the primary and the secondary contacts of someone who's already infected, the timescales for dealing with asymptomatics is assumed to be larger, twice as large as the timescales for dealing with symptomatic cases. Okay, so that reflects some additional difficulty in identifying asymptomatic cases compared to symptomatic cases. Okay, so run this program, what do you get? The first thing is that the initial number of cases that you start off with doesn't matter, this is known. All that number does is to shift the start of the epidemic peak. So the smaller the number is, the more shifted to the right is, but the value of the peak continues to remain the same. So that doesn't alter the number of people who are actually getting infected. So in a sense, that is good because it says that the numbers that you get at peak are not altered by any mistakes that you might make in your starting configuration. Those numbers are the same irrespective. If you change, again, standard results, if you change the infectivity, if you change R0, that has the effect of flattening the peak. And you can look at a bunch of different R naughts and imagine how the peak is flattened and how it shifts outwards. So all of these are standard results just to check that everything is going okay. Now you can ask, if you implement testing and quarantining on a population like this, what happens to the peak? And over here in these figures, the dark shade that you can see at the back represents the untested case, where you just let the epidemic run through without imposing any type of intervention. Okay, so in this case, the two curves that you see are with different protocols of testing and quarantining. One is a faster protocol in which we assume that you can test and quarantine a larger fraction of the population, say spread over 100 or 150 days. And the other is 100, 150, and 200 days. So these are the typical examples that we take. And you can see that the weaker, the more you spread it out, the more it peaks, the larger the number of people who are infected are, but it's still much less than the number that you would get if you didn't intervene at all. If you impose a lockdown and you ask what happens is that you just manage to shift the peak. You don't affect it at all. Because no lockdown is ever really truly effective unless you manage to have it last for at least 180 days or 200 days, and you manage to identify every single possible case within that limit, and you also don't allow for anyone to come in from outside. So all that lockdowns do is to really postpone the inevitable in terms of the number of cases. And that's again an example of what that sort of epidemiological lore actually works out to in this complicated model that I described to you. If you do lockdowns with quarantining and testing, then you manage to reduce the peak again significantly. So I had a number of about 60 lakhs earlier for the number of infected. I've now pushed it down to about 30 lakhs. If I have a lockdown and I couple that lockdown with a sequence of quarantining and testing, and depending upon the stringency with which I impose my quarantining and testing, I can push it down to fairly small levels. If it's the less stringent it is, that is to say the longer the time over which you spread it out, the larger the number of cases that you will wind up with. You can imagine different types of lockdown. So one lockdown was just switch the lockdown off, relax it, and let things go back to normal, and accompany that with quarantining and testing after the lockdown. You can also impose a lockdown in a light switch way, which means that the moment the number of infected cases crosses a certain limit, you impose a lockdown again. Then wait for it to go down. If it rises up and crosses again, then you switch it off again. So you can impose this threshold behavior by which you immediately tamp down and impose a lockdown if you have a threshold number of infected, and then you can see what happens to that. And this certainly reduces the peak, but it's not optimal in terms of the next scenario, which I will describe, which is a periodic lockdown. You impose a lockdown for 7 days, relax it for 5 days, 7 days, 5 days, 7 days, 5 days. And together with testing and quarantining, you can both delay the peak as well as reduce the number of hospitalizations. So now I've taken you through a bunch of different interventions that we have looked at so far in the first part of our work, all of which look at imposing different timescales for lockdowns, a light switch lockdown, a periodic lockdown, and as well as coupled to quarantining and testing, which has its own timescale over which you can manage to successfully test a large fraction of the population. And the real message that you should take from here, which I will emphasize again later, is that testing and quarantining is absolutely crucial to being able to deal with the disease. You can now look, for example, at Chennai, this is a typical city, and ask what happens with quarantining and testing when you apply it to Chennai. So the no interventions curve is on the left, and that's where you change the number of initial infected cases between about 10 and 460. Again, all that happens is that you shift the curves, and all of these curves overlap a little bit. So it's a little smudged out, that particular curve here. But if you impose quarantine testing on top of that, and fairly weekly, that's over a scale of about a year, you can see that there's a huge reduction in the numbers of people who are infected. So quarantine testing at the level of a city of a smaller population, which in principle can be well handled, has a large effect on controlling the number of cases that you might have. If you reduce that period from 360 days to 240 or 120, you really tamp down on that number. So if you can manage to ramp up quarantine testing over a period of about 120 days, the hospitalized numbers that you expect never cross more than about 450 to 500. You can see it increase during the lockdown period, then come down again. And then as you relax the lockdown, as the quarantine testing takes over post-lockdown, you can see that number never really rises, even compared to having a longer period of quarantine testing, 240, it's way reduced. So the numbers are about 500 compared to about 12,000 in that particular case. We then began to look at many more different types of lockdowns. So one lockdown that you can look at is what is called a periodic synchronous lockdown, where you allow 100% of the population to work for N days and then lock them down for M days. For example, if N is 2 and M is 4, you can imagine everyone going to work for the first 2 days, then be locked down for 4 days, work for the next 2 days, be locked down for 4 days. The second way you could do this is to have a staggered workforce. So imagine that 33% of the population works for N days and then goes to lockdown for 2 N days. For example, I can have G1 going on the first 2 days, G2, the second group, G2 working on the next 2 days, G3 working on the following 2 days, and then G1, the cycle then repeating. So this is periodic because it repeats itself. It's asynchronous because not all groups are there at the same time. And it's a lockdown because the groups go back to lockdown for the time that they're not allowed to go to work. You can see automatically that you have reduced contacts between people by reducing the number of people who are out to work at any particular day. And once they go back home, you maintain lockdown-like conditions. So this is a way of getting people back to work in a limited sense so that everybody manages to actually work, but it's applied asynchronously to the different groups. So you can look at this for a model city and ask what are the effects of this, of a periodic synchronous lockdown versus a periodic asynchronous lockdown. And it turns out that the periodic asynchronous lockdown or staggered lockdown is really the best option for people to return to work. And this is something that we have communicated to people who are thinking about decisions like this. What is the best way to move back to work to take a population? And the model very unambiguously suggests that the best way to do it is to stagger the number of people who are going to work. As I said, we put an age structure, and then we look at age-dependent fractions of those who will exhibit mild symptoms, and those of the fraction of those who are hospitalized, who will die as a function of the age bracket that they're in. And you can look at the changes in the hospitalization numbers. And for Tamil Nadu, they seem to be, these are the Tamil Nadu numbers here. And given these details about the age distribution across different age groups, you can see that you will have a larger or a smaller number, depending upon whether you include age structuring or you leave out age structuring. So that's an example of how you can actually predict what happens, the changes above and beyond the very simple non-age structured models that come about if you put an age structuring. So here is, as I said, we estimated R0 from the data for Maharashtra, and we started it on April 26, moved 22 days onwards, and then we relaxed the lockdown. So if you lift the lockdown on May 17, you can ask what is the trajectory that you expect given the current value of R0 and where the data seems to sit currently. So the data is that little dot over there, that's where we sit currently. And that would be the expected trajectory of the curve of cases as if you were intended to extrapolate it beyond that particular point. So that's the lockdown period, which is given by a calculation that terminates on the 26th of April. It includes data up to that particular point from a time series of the number of infected. And from there, you attempt to extrapolate outwards. We've also done a similar calculation for Pune, looking at hospital beds and the requirement for seriously infected patients under the staggered lockdown case, without the staggered lockdown, including variations in compliance. All of these are detailed, but again, this is the utility of the model, that if you can predict in a particular area, Hadapsar, Mundwa, or Bhawanipet, etc., what is the typical use of hospital beds, ICU units, ventilators, etc., that you might anticipate, that enables local governments to have a better idea of how to plan for that. So let me summarize at this point by saying that there are some basic messages from this work. The main message that I would like you to take back is that testing and quarantining together is really the most significant non-pharmaceutical intervention that you could possibly imagine. Many people have been saying similar things, many of us have said similar things about the fact that we are not testing enough, and because of that, we are not able to assess the level of infection within the population. So all of these calculations go towards buttressing that argument, that if you can test and quarantine adequately, if you can contact trace, even trace within the asymptomatic population by just expanding the level of testing that you can do, this is a way of actually reining in the progress of the disease very considerably. And it even works if you don't have an ideal, very fast testing up schedule. Even if you can test within 3 months to 6 months to a year, certainly within pockets where the disease is ramping up rapidly, that's actually a very strong hindrance to the progress of the disease. The second very specific statement that we make is that staggered asynchronous lockdowns is a way to open up post-lockdown. And so there we compare the synchronous lockdown with the non-staggered with the staggered lockdown. And we find that the staggered lockdown is really the best way to proceed. And if you combine a staggered lockdown with testing and quarantining, that really is the best direction in which you can possibly move post-lockdown. As you saw from the description of the model, among the current epidemiological models for India, this is the most detailed. It has 9 compartments. It sticks very closely to what is known about the disease in terms of the amount of time that you spend if you're asymptomatic, if you're pre-symptomatic, if you're strongly symptomatic, etc., your trajectory through the hospital, through your trajectory towards the final outcome of either recovering or dying. The main difficulties that all models will face, and we will probably have this discussion when we come to the end, when we discuss during the discussion session, is that all models need inputs of quality. And the main problem now is really having trustworthy data to base an initial condition on. And apart from that, we need better statistical estimates for many of these quantities. We are working with as good estimates as we can for beta, but they themselves depend upon data for the line list. They need a time series of the number of infected over a period spanning 2 to 3 weeks. Unless that data is good, and unless that data is trustworthy, unless we have a little more idea of what is the fraction of asymptomatic patients versus symptomatic patients, we really will not be able to proceed much further. So with that, let me just thank a whole bunch of collaborators. So Snehal, Bhalchandra, Mihir, Dheeraj, Pinaki, Shatabra, Anupama, and Vishwesha are people who sort of are at the core of this particular project. There are many others who've contributed to my understanding. I will not name them. Just be assured that there are large numbers of them. And this is, of course, ongoing work with this group, and we hope to expand the scope of what this model can do in the future. So let me stop with that, and thank you very much.
Thanks, Gautam, for the presentation. So we are way above time, so we have crossed 20 minutes. So yeah, so I'll just take 1 or 2 questions. So how many free parameters are there? Because this is, I think, an important question that everybody should respond to. And also, if you can say something, how testing strategies have been incorporated into the model at all, or can be accommodated and so on.
Yeah, so the real parameter is the beta parameter, which feeds into R0. And the assumptions go into determining what the C's are, because that tells you what is the level at which you can intervene in terms of testing and quarantining. And the beta is, as for all models, either you can call it beta or you can call it R0. It's really the same thing. But that's a central parameter that we use. We have some bounds on it based on data from Italy, China, US, et cetera, and even Indian data. And that's what we use. We use the time series of the Indian data to get a good example, good estimate for what that beta is. Was there a second part of that question, Pinaki? Sorry.
Yeah, so about testing strategies, how do you incorporate testing strategies into the model?
So their testing strategy, the efficiency of testing strategies are put into the quantity C. So we assume that testing is going to improve and become more broad-based in the future. That implies a certain trajectory for the quantity Cs that enter the model. Right now, we assume that it just rises exponentially over some time scale. Whether that actually fits a true testing regime is not very clear. And most likely it doesn't do that. It isn't rising exponentially fast, but is somewhat slower than that. And the question of adequate testing comes in the statistical estimation of quantities like beta. So that's a different question. How do you improve statistics in order to get better values for the beta that influences your R0?
Okay, so thank you, Gautam, for this nice presentation. So we now move on to the next presentation, which is by Om Damani from IIT Bombay. And he will be talking about tackling COVID-19 testing, tracing, social distancing, and hygiene. So Om, you can start now.
Yes, so let me share my screen. Good afternoon, everyone. Hi, good afternoon. Everyone can see my screen? Assume. So yeah. This is joint work with my colleague, Professor Jayendran Venkateswaran. The two of us have developed it together, practically sitting all the time together for a long period. And of course, with support from Dr. Tarun Bhatnagar, Dr. Giridhar Babu, and a whole bunch of current and graduated students, PhD students whose names are given there. So the big question for us first is, what is the goal of the model? As soon as we started thinking about this problem, that what should we be doing? And really our goal was not what will happen, because what will happen depends on what we do. And so therefore goal was, what should we be doing? This seems such a big crisis. So the purpose is, what if, by the way, do remind me after 10 minutes and 15 minutes if I forget. I'll make sure I stick to the time. So the goal is what if scenario analysis to compare intervention, given that there is uncertainty in data. So there is so much debate about what's the real number of asymptomatics out there, or even the symptomatics. We are only all the discussion about testing and everything, everybody knows. So similarly, the model so many of the model parameters are still debatable or may depend on the geographic condition, socioeconomic conditions, and so many other things. So our real goal was to compare the relative impacts of interventions and intervention combination. And we believe that even if there is uncertainty in data, but we can with high confidence know which interventions are more likely to work than others. And so that's possible as long as data and the parameter we get the relative values right, not the absolute value. Of course, there were a lot of philosophical issues and conflict we were facing with ourselves, with others, as we were discussing. First big position to take, which modelers understand, but whether to go for absolute projections at all or not. That is, if we track real life data and then we say, okay, based on this is how many infections we'll have, how many deaths, how many hospital beds sorted. As we were interacting with some government officials, some other people, we realized that no matter how many disclaimers and qualifiers you put, people need absolute number, they want absolute number, I don't know whether they need, and they will just going to lap it up. So that was one conflict we are facing, whether to how much emphasis to give to absolute number. Other is, of course, the whole issue of lockdown, the socio-economic impact of COVID, non-health, and health impact on non-COVID patients. Like what happens to the TB patients, what happened to the heart stroke patients. And finally, for whom are we modeling? Who is our stakeholder? Which community are we targeting? Do common toilets, as in Dharavi, figure in our model or not? Personal protective equipment for all essential service providers, or at least for the healthcare workers, do they figure in our model? So, I mean, just looking at, all the, we also do the sort of the standard SIR like model. What's the role of air conditioning? Is there a reason that the developed world and developing world, the trajectory will be very different and we can't just take their model? What about public transport? What kind of prediction we should do for Bombay without talking about local trains in Bombay? And population density and what is going to happen in Dharavi? We were asking that question before the thing started. I'm just saying these are all the questions for most of which we had no answers. And we were conflicted. We did some of them. We did not do, pretty much most of them we didn't do, or we did them in ad hoc way. Anyway, a lot of things happened based on these issues, these questions. But should these questions appear or not appear in our models is a big question. So, and therefore, one is for which community you are modeling for, another is who is the audience. Is it your scientific colleagues? Is it the policymakers? Is it the common people? Is it the community that's getting affected that you are trying to model? Are they even in a position? So what should one do? Those were the big questions we were struggling with. Anyway, so coming back to modeling, so we follow the system dynamic, what's a methodology called system dynamics that emphasizes capturing real world processes, causal pathways. It says the model behavior must be generated by the endogenous feedback, not just by external interaction. So, and the entity flows in the model must respect conservation law over various resource constraints and various delays. And so all the parameters would have corresponding real world things. So some of the seminal work in this area have been the world dynamics model in 70s that came with the phrase limits to growth and was a big instrumental in the environmental movement. And the current C-Roads world climate change simulation model are based on this system dynamics philosophy. So anyway, so what we have is a detailed age structured model. There are 16 age group of 5 years each, and the interaction between each model is taken as per the age group. And we talk about various disease transmission pathway, expanding significantly from the standard models. And then model was calibrated, but not for projection purpose, but mainly for structural validation purpose. And then and our goal was to model the interventions and simulate it. It's a community transmission model, like most SAI model, though we discussed this issue of cluster transmission, but cluster not just in the sense it has been discussed. But like I said, if you think about the issue of comorbid air conditioning, issue of how close two people are when they interact with each other, and all of that, whether there's a ventilation in the house or not. So that, or in an event, like even is a lot of big public events, whether it been, whether various religious groups or social groups, the transmission have happened. So in that sense, a cluster transmission, not in the sense discussed so far, because that is appearing as is important, important mode of transmission. Okay, So anyway, this is a very picture of very high level model. So by the way, sorry, can I get rid of part of my screen itself is probably showing the Zoom speakers. Is there a way to get rid of it? It hides part of the model. But anyway, so this is a very high level model. I will break it down. I will talk about it in more detail. So my colleague Jendra is also here, and I guess he will jump in as and when needed. So, so first is the disease transmission model. So what is the basic disease progression? As discussed just now by Sumit. So we have susceptible that become exposed, then become asymptomatic infective, then become infectious symptomatic, and after that they may, and at each of these stages they may be recovering without progressing to the next stage, or the disease keeps progressing. So then some people will need hospitalization. Within hospitalization, they may need to go to ICU, and then finally, hopefully, they recover or some fraction would die. That's the very basic disease progression model. So on top of, now we have modeling the infection rate. So if you look at this part, this is where the main infection happens. So the infection, of course, and I will talk a little more in detail later on. But essentially, it's a function of infection from all these different compartments. So all the infective people are along this different compartment. And so we also model the contact rate and the interaction rate. So age group and contact rate between them. So these rate things are interventions, so we can ignore them for the time being. So for each age group, you see what is its contact rate with various age groups, and how many, what fraction of that population may be infected and at what different stages. So that sort of gives us the total interaction, and then multiplied by the infectivity, which itself may be affected by various other factors. But that's the key model of, that's our model of infection rate. So infectivity is probability of an infection upon interaction between an infected person and a susceptible person. Contact rate is the average number of persons a person interacts with in a day. Of course, it's really ideally the average number of interactions. And then, so given all these compartments, you have to do a global sum over it. So for each age group, compute infection from each other age group. So for example, if you focus on one particular age group and you say how many people are going to get infection from symptomatic infections. So this is just some formula without going into detail, but essentially you ask how many people are there in the target age group, what fractions of them are in that symptomatic infections, and then contacts per day, what is the, so you sum over various types of contacts, and that's how you, so this is just one interaction between one compartment and one age group, and then you sum over all age groups and all compartments. So that gives that will look something like this, but essentially it's a summation over all of this. So various, so that's the infection modeling. And then infectivity, like I said, how close you are, whether you are using the mask or not, how much distance are you maintaining, all of that will affect the infectivity, which is the probability of infection during an interaction. So that was the model. Then the other intervention, the most important, quarantining and isolation. So that is this part of the model now. So earlier I showed you the top of the model, which was the disease progression stage. So we assume now while you are infected but not hospitalized, then so you are, let's say you are at home, say let's look at the infectious symptomatics, and then either as a result of testing you may be isolated, or you may quarantine yourself, or all your contacts may be quarantined, right? Because as a result of contact tracing. So the key point is that an infectious symptomatic person either may be isolated or may get quarantined, or it may be awareness impact that I am now coughing, and because I'm aware about COVID, so I may just quarantine myself. So isolation means I have tested positive, and then maybe I'm in a hospital facility or a very well isolated facility, whereas quarantine means I may be at home quarantine or institutional quarantine, depending on how I was discovered, but my degree of isolation would be little less than if I was positive. So while quarantining, I am infectious, but I may not know it. While isolated means I know that, I have tested positive. And as a result of contact tracing, the asymptomatic infectives may also be similar. If the asymptomatic infectives are tested, then they may get isolated, or they may quarantine themselves as a result of either awareness effort or a result of contact tracing. So when somebody tested positive, some fraction, a good fraction of their contacts may be asked to quarantine themselves. And then, of course, disease progression pathway will take place while you are in these compartments also. So that is roughly the main model. We also model hospital capacity in detail. Here, the main concern that was raised to us a month back was the issue of hospital overflow. So if you see that there's a demand on hospital, so this is sort of, you can add this to the bottom part of earlier disease progression model. Main thing is, okay, so now earlier model will generate certain numbers in each compartment, but hospital now we introduce only finite capacity. So there is an overflow, and of course, this overflow has to be as per the age groups and other things. And then while in the overflow state, we may, again, either one may recover or one may become critical. So the parameters are changed slightly so that we assume if you are not getting medical care that's needed, then your likelihood of disease progression to next severe state becomes higher. And similarly, the probability of needing ICU or ventilation or dying increases. So this is the hospital capacity model. Anyway, so with that, I think a lot of these other details have been explained by the earlier speakers also. So within each compartment, other than this age group and contact structure thing, population is homogeneous, well mixed. Okay, we also have 4 contact spheres to test various interventions, which is home, work, school, and other. And these interactions are age dependent, like we said, in each of these 4 contact spheres. And so there are various other interactions, but we do not have a mobility module. So the All India, the interaction is, the mobility is assumed to be implicit in this. And while calibrating the lockdown, we assume that interaction at work reduced by 80%, and at school by 100%, and in other zones by 70%, because people have to go out for essentials. And these are some of the parameters that were picked from literature and then slightly calibrated based on just the initial period data. So age and zone is the contact metrics were picked from Prem et al. And we actually apply a multiplier to it. I will talk about it. We believe the asymptomatics in the second bucket are going to be infecting at half the rate of fully symptomatic for those 48-hour period. And there is a base infectivity. So there are different delays that we have gathered from various literature. Okay. So now the main goal of the work is to talk about what should be done, like we said. So as earlier speaker talked about, the basic reproduction number R0. Our use of term C is slightly different from earlier speakers, so just please pay attention. So for us, for this disease to die out, of course, the reproduction number should fall below 1. C is number of contacts or number of interactions per day between an infected and susceptible. It's just the number of interactions. I is the infectivity, the probability of infection in such an interaction, and D is the disease duration for which a person stays infectious. So the C and I values were taken for literature and then tuned. But also note that in the model, the product C into I matters, and that's why other models use a single parameter. So, and I'll come back to that. So slight change in value of C can be compensated by a change in value of I. So, but this does give us why distinguish between C and I? Because it gives us 3 different types of intervention. Infectivity, that is the probability of infection during an interaction, can be reduced by social distancing, right? By maintaining 6 feet or what as many feet as you can. Use of mask, personal protective equipment if you are essential service provider, washing the hands, all the better personal hygiene, taking a bath. You have come out from crowded. Again, who can afford it and how much can they afford it? Like I mentioned, those are separate questions. Whereas reducing C, which is the number of interactions themselves. So this is social interactions at home or outside, or reduced level of contact at school or work. And in different sphere, you can reduce it differently. But point is, lockdown is of course one good to say, but various more granular policies for each of these spheres can be designed. And then D, the duration of disease when one is infected. Of course, they need medical interventions that are outside the scope of our work. But we say that contact tracing, isolation, and quarantining is effectively achieving reducing D. That is the number of days when a person is infecting others. So that sort of says that if we look at this basic equation, this gives us 3 strategies to reduce C, I, and D, we say, and how to reduce each one of them, and of course in combination. And then now this R0 is the basic number. As we intervene, then we want to compute the dynamic RT, the actual reproduction number, and we simply model it as, of course, this using average over. So infections per day divided by the number of infective from all the compartment, and then we can multiply that by the disease duration to get the running RT. So
Om, your 15 minutes is up, so 5 minutes left.
Okay, sir. Okay. So very quickly then, so these are the 3. So I won't go into the detail here, but mask use, physical distancing, personal hygiene, contact reduction. Only thing is contact reduction is granular. So our parameter will change value at home, school, work, and differently, we assume, because our goal is to open the economy. So the work is, it's essential to open the work, and that results in certain other interactions. And schools also have to be open. How long can you keep the schools closed? While we can reduce more interactions at home and social functions, gathering, or general avoidable interactions. Contact tracing and isolation, again, there is a parameter that refers to the fraction of patients that can be isolated within 2.5 days of onset of symptom and a corresponding fraction of their quarantine. So key point here is now to show this. We tune the model, calibrate, and so base case we find R0 to be 4.8 based on that earlier calibration of the data. That is with a certain value of this social distancing and contact tracing and isolation. That's just the calibration. So you get some value for base case. Now you say I can make each one of the interventions. What if I only promote heavily the mask use, physical distancing, and hygiene, which is an individual can do? Or we do contact reduction, which is like work closure, school closure, or a fraction, whatever is being discussed. Or the other third policy, CTIQ, which is the contact tracing and isolation. And then what you find, then we pick those values of these reduction parameters, so shown on the left, 0.4, whatever these values, that bring down the R0 from 4.8 to 2.6. So this was just for a uniform comparison. Then we say we can combine 2 of these interventions. So when we combine the first 2, we get 1.43, similarly 1.33, and so on. And finally, if we combine all 3 interventions, then the R0 value comes below 0.92, comes to 0.92. So below 1, that means that the pandemic can be contained. So the important point here is, of course, we don't know, we have picked some value 0.73, 0.44. In practice, what happens? The key message here is that all of these are important. Any one will not do, because of course you cannot do it to the 100% success. So all 3 must be done. They must done to the extent, and that then a success is possible. It's not all doomed. Pandemic can be contained if we aggressively pursue promotion of mask use, physical distancing, hygiene, along with contact reduction and contact tracing and isolation. So since I don't have much time, I will skip the calibration questions, and that was not also the focus of our work, because that's not the projection, but it was to get the initial estimate for the models. And then, of course, like I said, all the charts are there under various policies, the absolute number of infections and all the parameters, but I would like to leave time for interaction. So there are a number of policies we have simulated, and in addition to those 8 that I just discussed, which is the granular combination of those 3, then we can vary parameters for each of those 3 policies. So there are various combinations, and even a rising graph like this, these are for various states, whatever our models show, but a rising graph like this, still it reaches an asymptomatic limit. So it's not, it's still the pandemic is in control. It's not, I mean, it's going to give us a very long time, even if, because the pandemic can be controlled at a very high level. So what we don't know, in my opinion, but are very important, is this infectivity, modeling infectivity that we also don't know and nobody else talked about. Duration, manner, and intensity of interaction. Just because I come in contact with a COVID positive patient doesn't mean I will get infection, right? So there is so much literature on it, how long they are, how close should you be, how much should you be talking, the issue of airflow, and there the role of air conditioning. When we take Western world model, versus developing world, I think the issue of air conditioning, centralized air conditioning will become very important, and why it spreads in a the clustered environment. And then the dwelling density, ventilation, issue of common toilets when we talk about Dharavi or most of our urban area, Mumbai, Ahmedabad, the slums, because and there are many reports that the infection is spreading from common toilets and the house, in small house, if there are 8-10 people. So where should our focus be? And these will all determine cluster impact. So I think these are very important things that we don't do, and probably so far others also don't do, but something that needs to be done. So to conclude, we believe that pandemic can be controlled with all the three measures. Of course, with the contact tracing, isolation, and quarantining, but promoting improved hygiene, use of face mask, social or physical distancing, and PPE for this we have been raising for a month. The personal protective equipment for all essential service provider be critical, and then reducing contact at home and non-work, non-school. Work and school, some minor adjustment we assume, whereas home and other sphere. So that's, yeah, with that I would like to end saying that if we can put all of this, the pandemic can be controlled. Thank you. Thank you.
So thank you, Om, for the nice presentation. So one quick question. So I mean, this is a technical question sort of. So what is the impact of mask use? That is evidence to back up the values that you're using for mask use impact. So for any intervention that you're using, how do you input the parameters?
So that's we showed in the table, and we can say these things, right? So this is the base case calibrated. So this was just to say that, look, since the lockdown has started, people had started using masks, people have started doing social distancing, there is some awareness. So if pre-lockdown we assume to be 1, we sort of calibrated it to 0.8, which means the probability of infection during an interaction reduces to 0.8 if you are maintaining social distancing and some degree of mask in the early days of lockdown. Now with more and more awareness, and like there are different type of masks, we read all the reports and also discussed with doctors, they were all saying these masks, usually they say they can reduce by up to 50% or whatever. The issue of homemade mask versus surgical mask and all of that. Sorry, I'm not sure if I answered your question. But, so the mask use is it's a mask use combined, mask use, distancing and hygiene, all three. Right? Also the fomite transmission, we have like if you come back home and wash your hand, that's not modeled in any of the SIR model, but we presume it gives you some benefit. So all of that, the hygiene, distancing and mask use together, we take it as a multiplicative factor.
Okay, thank you. So there's also a question about deterministic models. Maybe we come back to that question later on when you have a panel discussion among all the speakers. So thank you, Om, because we have really crossed a lot of time. So maybe we move on to the next speaker. So the next speaker is Sai Vignanampati from IIT Bombay, and he'll be talking about another compartmental model for India-centric interventions against COVID-19. So Sai, are you ready?
Yes, I'm ready. I'm just waiting on Om to stop sharing so that I can.
I think you can just start sharing it.
Okay. Okay. Can everyone see?
Yeah, we can see your screen. Yes.
Okay. It's still. There we go. Okay, thank you, everyone, for joining us today. So today I'm going to talk about the model that Mithun Mitra, who's in this call right now, and I have developed in conjunction with a lot of authors who are on the screen. For brevity, I won't mention all of them. I just want to draw attention to Kem and Vandana, who are actually in the ISRC group, and Aritra Giridhar and Tarun, who are part of the ICMR team. So with that, let me just get ahead with what our model is about. What we wanted to do, the overview of what the model tries to accomplish is the following. So it's a generalized SEIR model, just like many of the other talks before us. But it includes testing fraction, age stratification, and it tries to incorporate the states. And I'll talk about that as we go along. It explicitly models the lockdown as well. It incorporates uncertainties and heterogeneity in the testing rates from different states. It also incorporates district level modeling. It incorporates realistic transport data. So this is something I'd like to emphasize. And it incorporates some Bayesian techniques to make predictions with requisite uncertainties. So we hope that when we've converged on this model and when the work is done, that we can open source this code at some point so that it can be peer reviewed thoroughly, and it can also be borrowed and extended as people choose fit. So that's the overview of what the model tries to do. The policy questions that we asked ourselves was basically, what is the impact of a targeted lockdown? So this, we're essentially in the middle of one right now. What's the relative importance of testing versus lockdown? Because this is, something that was also, I think, of interest to study and then to kind of highlight for people who are interested in the policy circles. The relative importance of distancing versus lockdown, and also trying to predict developing hotspots. At least qualitatively predict developing hotspots, so that targeted interventions can be applied to those hotspots. So those were what we were going after. So I'll show you some results. So let me begin by describing the model. So you've seen many SIR type models before. So I hope that the diagram is somewhat self-explanatory. So we have a generalization of an SIR model. But what I want to highlight is essentially an important term here, which is a compartment here, which is this P compartment. Which is this P compartment in the middle, and that's the number of people who've tested positive. So that's something that I want to emphasize, because the tested positive is a number that we can then compare against the reported data. So just like all the other SCIR models, we have a susceptible compartment, we have an asymptomatic A, we have an infected I, and an asymptomatic, we have a pre-symptomatic A and then asymptomatic E. And what we also model, these are in the X compartments, which are given below, are those exact same compartments under lockdown. So by switching on or off the lockdown rates, kappa naught and mu, what we can do is we can transfer people from, let's say, a susceptible compartment to a susceptible compartment that's under lockdown. And then after a certain time, we can release them from the lockdown back into the general public. And so likewise with the pre-symptomatic, which is the A compartment, the asymptomatic, which is the E compartment, the infected. The people who test positive, their only route in this model is to go to the recovered or the removed compartment R. So that's the basic idea of the model. And different rates that are involved in the model are also presented here. So what we've also done is we've age stratified the model, but we've age stratified it to 3 age groups. So less than 20. So these are basically children and young adults who are going to college. The 20 to 60 basically is the workforce population. It's meant to be a proxy for the workforce population, an approximation to the workforce population. And so that all of the transport basically happens in this workforce population. All of the work transport happens in the workforce population. And then over 60s, which are folks who we are worried about from looking at the mortality data and so on and so forth. So the age stratification is implemented in a somewhat simplified manner, but it captures all of the essential details that we would be worried about when we are trying to make policy, for instance, for those who are making policy. So here are the equations. I've exchanged this in a previous slide set before, so I'll just move on. So the question that was on our minds, and perhaps is on your minds, is how are testing fractions obtained, right? So where do testing fractions go into our model? So let me back up just one second. There are 3 rates, kappa prime, kappa, which is indicated in green, it goes from I to P and Xi to P. Kappa prime, which goes from E to P and Xe to P, and kappa double prime, which goes from A to P and Xa to P. So these 3 rates are testing rates, and these testing rates are basically determined from testing fractions. So our model, what it does is it accommodates basically the heterogeneity of different states. So this is a known fact that different states are testing at different rates. And so we wanted to put that into our model and study the effect that that has. And so kappa T prime and kappa T double prime depend on the testing fractions, which I will get to in a second. While I'm on this slide, let me just mention, this was a question that often arises that arose in all the other talks. So there are two fitting parameters for our model. So for every unit cell that we construct, so if I want to model states in the country, then each state will get a beta and a beta 1, which are both fitting parameters, times the number of states. If I'm modeling districts in a state, then it's beta 1 per district times the number of districts. So that should clarify the number of parameters in the problem. Beta and beta 1 can actually just be read off from the diagram here. Let me just emphasize that beta 1 is actually the effect of an imperfect lockdown. So beta tells you the rate at which susceptibles go to pre-symptomatic, whereas if we are in a perfect lockdown, of course, then the moment I put you in lockdown, I put the person in lockdown, then excess should not be able to travel to XA because there should be no way to infect somebody. But because lockdowns are imperfect, given the kind of the duration that this disease is pre-symptomatic for, and given the imperfect nature of life, the beta 1 parameter essentially models the imperfect lockdown. So these are the important parameters. There are others which I'm happy to discuss offline. So now we need to determine what the testing fractions are, and this basically we relied very heavily on Professor Shorendu Gupta's preprint, which I've cited here. And so I'll just walk you through the argument here. So the case fatality rates, CFRs, are determined essentially as the ratio of the number of deaths to the number of deaths plus recovered. And so what you do is from this, you can basically, you can write basically a measurement error rate, which is on the screen, which basically models the ratio of the true number of recoveries to the reported number of recoveries. And so you can invert this basically and write basically this quantity xi as basically rho times 1 minus CFR by CFR, where rho is basically obtained from the reported data. So it's a D over R, and it's obtained from the reported data. We pegged CFR to the to 2.3%, which is numbers that the World Health Organization released from their study of the Chinese data that was available. And so the testing fraction is of course 1 over this quantity xi. So so from this, what we can do is we can go to each state and we can look at the D and the R numbers, and we can put those in. But there's one more thing that we did, which is that we tried to incorporate two separate pieces of data which will inform basically how well testing is happening. One of these is on the left. It's basically the number of tests per million. So each alternate state is actually labeled here. And so Delhi, which sticks out, I've just labeled it separately. And on the right-hand side, you have a different thing, which is basically, it's called the health index. It's a number that is released by the Niti Aayog. So the report is attached, is referred to for your, for you to look up. And so both of these basically are important factors. Why are they important factors? Because of course the tests per million directly determine the number of people who are going to actually show up as positives in your data set. And so that's important to incorporate. But there is another factor, which is this health index. And health index, what it is it's a proxy for how well prepared these states are for pandemics. So by looking at other pandemics, basically Niti Aayog has come up with a number. It's like all numbers that are trying to quantify complex phenomenon. It's imperfect, but we went with it. And the number basically tries to just inform you as to which the better prepared states are and which the less well prepared states are. So we folded these two numbers in and we arrived at this kind of this method of calculating the testing rate for a state. So what we do is we take the D and the R and we calculate the rho, and so we just watch for the time series to settle down a little bit. And the imperfect nature of the settling down you can see on the graph that I've presented for Kerala. And so from that we extract rho Kerala, which is 0.06 for this. So you just just draw a straight line somewhere and extract this number. And by using that, you can calculate basically what the testing rates are. So why is Kerala singled out here? Because what we basically assumed was that Kerala's data is very reliable. It's the best performing state in terms of healthcare preparedness, in terms of many other socioeconomic factors, which means that if you have to rely on any piece of data from any part of the country, we should first rely on the Kerala data. So what we did was we pegged all the other states' testing rates, testing fractions, to actually the Kerala number. So you take the Kerala number, which is the equation on the at the bottom, F Kerala. And then what you do is you take the ratio of the health index of the state to the health index of Kerala. So it essentially tells you how well prepared is the state in comparison to Kerala. And you then take the test per million of the state to the test per million of Kerala. So you can pause and ask why was health index separately taken from the test per million? And the reason for this is that some states, even though are somewhat in the middle of the ranking order in terms of their health index, have actually stepped up and tested far more than one would expect them to, which is good. And so we wanted to make sure that this variability in the governmental response is also indicated in our state testing rates. So that's the way that we calculated the testing rates, and then there is some simple algebra that connects it to basically the testing fraction Fs. And then there's some simple algebra that connects it to the testing rates, kappa t prime, and kappa t double prime. So that's about that. So just to make sure that we were doing things sensibly, we tried to directly estimate the testing rate for Kerala, the testing fraction for Karnataka, and indirectly estimated from our method, and the numbers seem somewhat consistent. So I think if we are off the mark, we're not off the mark by much, is the way I would say it. And so that's the technique that we've used to compute the testing fraction. The other thing that I want to mention is that due to our colleagues, thanks to our colleagues, Avijit Maji, Sandeepan Roy, and MD Sushma at IIT Bombay, we've been able to incorporate basically the district level transport matrices for all of the districts in India, essentially. So the way this works is basically it uses worker population ratios and trip length distributions, and uses GIS maps and so on and so forth to do this, and then estimates essentially the number of people traveling as rates going from one district to another. So the district level transportation matrix can be used to construct the state level transportation matrix, and likewise you can push it out to the country as well. So it allows for simulations which are actually pegged to the actual transport that is happening, of course, before lockdown, and allows for the simulation and forecasting to happen. So what this allows us to do is basically, given this underlying transportation matrix, we can of course reduce it by some level to model basically partial lockdowns and so on and so forth. So that's something I just want to point out as well. And the one of the final things that I want to mention is how do you discuss basically how do you estimate what the trajectory is. So we used some standard techniques that exist in estimation theory, which is what's called a Kalman filter. So it's a predictor corrector type mechanism or type model, or a recursive Bayesian estimator. And so we just use the recursive Bayesian estimator to try and lock onto the correct trajectory. So just as an example, on the lower right-hand side, you can see a diagram where the true trajectory is basically in the green, the red, and the blue. It doesn't matter what the compartments are. And then the green, thick green shadow is actually an uncertainty region that's given, and then it locks onto the correct trajectory given the data. So that's the thing that we've used. Before I get carried away and try to make any kind of statements about numbers being taken too seriously, I put a warning for myself, which is that there are lots of assumptions, simplifications, and limitations of the model. So there's the typical compartmental model problem. There is various parameters that have to be that were taken as median values as opposed to the distribution. Mortality is estimated essentially pegged to some date. So the nonlinear Kalman filter that we use, the extended Kalman filter, is not a blue, which is a technical point which I'm happy to take up, so on and so forth. So so we should take the results that I'm going to present to you only as qualitative statements and not quantitative statements. So with that, let me just talk about the interventions that I'm going to present to you today. So the interventions are three interventions that I want to present to you. The first is just the baseline scenario, lockdown till May 3rd, nothing afterwards. The second is intervention number 1, which is basically health index pegged testing. So this is something where the lockdown ends on May 3rd, and then no colleges till the end of June. Rank states according to 3 partitions of their health index. So Kerala is on top, and then what we do is basically the top move to Kerala's testing rate. So it's not it's unusual, but it is not unrealistic because Kerala in the country is already testing at that rate. and the middle moved to 50% of Kerala, bottom to 25% of Kerala. And the last intervention that we wanted to check was a very heavy intervention, a heavy-handed heterogeneous intervention. So this is where the entire country lockdown is till May 3rd, and then no colleges till the end of June. Reduce all contact matrices to 50%. So this basically models some sort of reduced contact with which work can be allowed. So this, you can interpret it whichever way you want. Transport matrices are reduced to 50%. So essentially all the non-essential workforce is asked to stay at home, and office work is somehow managed by a reduced workforce. Lockdown a state or a unit cell, a district or a state, if the number of positives divided by the total number of the population of the state crosses 0.01%. So this is a very harsh lockdown, basically. So this is a vigilant government that's looking for positives, and the moment there are positives, it locks everything down. I want to note that this is not a government that is testing at unrealistic rates. These are still testing at the same underlying rates. So with this, let me just quickly conclude by showing you a couple of results. So what I've presented are three states, three interventions for Kerala. So the no intervention is on the upper left-hand side, then intervention 1 and intervention 2. The only qualitative thing that I want you to take away from this is that, so the percentage of the population goes from 6% if no interventions, 3.5% if the intervention 1 is imposed, and 0.001% if the intervention 2 is imposed. And the uncertainty curves that you see come from the estimators that we used. West Bengal, on the other hand, basically 60% if no intervention, 35 if there is intervention, and somewhere between 40 and 45 if intervention 2 is imposed. The region that is shaded in pink is where the heterogeneous lockdown is imposed on West Bengal, basically. So the simulation is run for the whole country, and this is just the West Bengal result I'm showing you. Here is a state which is basically somewhere in the middle. So Gujarat, 40-45% if nothing is done. This is the infected is in the green. Roughly 25% if intervention 1 is imposed, and 0.02% if intervention 2 is imposed. So likewise, what we did was we took our model, as I've said, can be also deployed for a state and its district. So we took the district level simulation for Karnataka, and so sorry, even though the diagram is for Maharashtra. So here is Bangalore, and you can see basically this was just no intervention. So this was just an analysis just to see if we have the numbers are even making any sense. And the numbers, so this is an older simulation, so the data is only like 18, 19 April. But when we looked up compared our numbers against the current numbers, they're somewhat sensitive. They're still sensitive. So the simulation is not completely out of character in terms of predicting. Here is Mysore. As you can see, the number of positives tested are in the reported data from India COVID-19 is in the red. The blue is our model's positives, and the green is our model's infected. And Udupi for what it's worth, you can just look. And so all of the districts are simulated this way for Karnataka. So let me conclude very quickly. So increased national testing and quarantine, like many others have said before me, offer some of the best strategies for us to combat the spread. Heterogeneous lockdown with these aforementioned strategies plus physical distancing, which is modeled as a reduction in the contact rates, is very effective. States with good testing and health infrastructures control the epidemic effectively in the lockdown period. Post-lockdown, migration from underperforming states can negatively impact the health outcomes of the states which have good testing rates. So we've seen that in our simulations as well. So this was something that I think is a conclusion that is quite in keeping with the other things. I just want to mention there are many assumptions that I've already outlined. So we are trying right now to fine-tune the variances of the estimators to make things better. We're trying to basically take on district-wide simulations for the whole nation. So that's a little bit of a complicated run. And we're trying to generalize the median parameters, which we've just pegged to realistic probability distributions, among other things. So thank you very much, and I'll take questions.
And Sai, for the nice presentation. So one question that has come up is about the use of the Kalman filter. So it's a question from Prashant Kumar. So he says that the implementation of the filter needs error in model, initial state, and observations. How do you calculate these values?
Yeah, so we just peg them to Gaussian errors because otherwise you're in real trouble. So this is a fair point. So let me just explain what we wanted out of the, what we wanted to do with the Kalman filter. What we wanted to do was something that Professor Menon mentioned in his talk, which is that the initial conditions of any deterministic model are not particularly well known. And so this is a problem that, that already exists in various other branches where you're trying to shoot down a flying plane, for instance. And so these estimators essentially just manage that uncertainty. So what we did was we put, we first of all assumed Gaussian probability distributions for which the results are somewhat nice. And then, so it's an unrealistic assumption if you want to challenge me on that, even though for large numbers maybe it's okay. What we did was we took the uncertainty region large enough so that the results were somewhat trustworthy. What do I mean by this? So if I go back to March 1st and I want to say that there was 1 person infected in the country, I give it basically plus minus 15, 20 people, so that, you know, that's a more realistic assumption than just saying one person is affected. So so that's the way in which we like the Kalman filter better.
Okay, so thanks, Sai. Thanks for the nice presentation. We have to stop here because we are running 20 minutes behind time. So we have to finish in time. Yeah, thanks.
Thank you very much.
Yeah. So next speaker is Girish Setlur. Girish, are you ready? So Girish will be talking about modeling and simulation of COVID-19 propagation in a large population with specific reference to India.
Good afternoon. I'm Girish Setlur, professor at the Department of Physics in IIT Guwahati. I thank the organizers
Can you speak a
of the
bit louder,
ISRC
Girish?
Symposium for inviting us to represent IIT Guwahati. ISRC stands for Indian Scientists Response to COVID-19. We at IIT Guwahati of ISRC to provide rational, timely, and accurate information about COVID-19 that is easily understood by the public at large. The importance of this effort in combating fake information rooted in superstition and other unacceptable belief systems cannot be overstated. I represent the team that comprises 3 extremely hardworking and bright BTech engineering physics students. Commendable efforts to learn the basics of this subject on their own and also design and solve compartmental models with features that are quite new indeed. They are Ashish Menon, Nitin Rajendran, and Anish Chandrachud. Those who are new to the field of mathematical epidemiology in particular and mathematical biology in general may be amused and somewhat skeptical to see complicated mathematical equations describing living systems. While the relevance of a mathematical approach to epidemiology should not be overstated, given the large number of simplifying assumptions it entails, it is remarkable that simple, well-motivated mathematical concepts known as compartmental variables and rate equations involving these quantities are quite successful in reproducing a number of salient features of epidemics. Terms such as herd immunity, carrier population, etc., that are now heard in news briefings when earlier they were confined to scholarly conferences or in these. So in this slide, I'm going to tell you the questions that we addressed in this work that we have posted on medRxiv. So the first question that we addressed was, why is it necessary to mathematically model this pandemic? The second one was, how would COVID-19 affect India once the lockdown ends? So the third important point, which one in India? Then what are the policies and decisions, for example, with the epidemic And this is very important because we don't want to what extent and lastly, the question was, how does migration affect the pandemic? In other words, migration across different states. So that's the one thing we have considered. Okay, so in this slide, I describe the relevance of our work to, in general, to society and to the academic literature of epidemiology. So you see, to society, it's very relevant because we can see through our various sources, COVID patients affected by this ailment worldwide, with nearly 2.6 lakhs deaths due to COVID-19. And in it, there are already upward of 1,700 deaths and counting. So our work is significant because we are able to study in detail various aspects such as the nature of the pandemic in India before and after lockdown. And it, generally speaking, underscores the importance of investing in basic health infrastructure. So as we'll explain, the importance of describing the mathematical modeling of COVID-19 epidemic, and is to introduce what are known as compartmental mathematical models, logical systems. The salient features of these models include the populations involved are assumed to be divided into compartments. So in other words, the affected population, the population affected by the epidemic is assumed to be divided into compartments. And so to give you an example, the compartment could be susceptible individuals, infected individuals, or individuals that have recovered from after contracting the disease. So this is the simplest compartmentalization you can think of, and that's the so-called SIR model, which is one of the oldest models dating back to the late 20s. So the rate of transfer between the compartments are modeled as time derivative of the compartment population sizes. And the coefficients of the coefficients that appear in these equations have to be, they are not derivable from the theory or the from these phenomenological models. They have to be obtained by fitting actual observational data. So the epidemic is modeled as a set of differential equations, and of course, this is not physics, so we'll have to make a large number of simplifying assumptions, and most of these assumptions have to be tested on the field, and they cannot themselves be derived in any way. Okay, so let's get on with the basic point I was trying to talk about, namely in our case, how have we modeled COVID-19, to be specific to India. So the way we have modeled COVID-19 that's specific to India is by introducing the following compartments. So the first compartment we discuss is the susceptible individuals that are susceptible to COVID-19 infection. Then the second compartment is the number of individuals exposed, but they themselves are not infected yet. And IS corresponds to the infected individuals who show symptoms, the symptomatic infected individuals. Then there is the other fourth compartment, which is IAS, which is the infected individuals who do not show symptoms, so they're asymptomatic. So you can see that there are a large number of compartments that one has to deal with if you want to make your model realistic. So the fifth compartment is infected individuals who are now in quarantine. But then we decided that it would be better to distinguish between two types of quarantined individuals. One group who have just entered quarantine, and the other group is individuals who are severely infected and who have entered quarantine. So you might be wondering why there is such a subtle distinction. You'll see later on when we discuss our flow chart that these two compartments flow into different daughter compartments. So, so the seventh compartment that we are introduced is what is known as the carrier compartment. So these carrier compartments are infected individuals who were wrongly diagnosed as having recovered by the hospitals and discharged. So that is important because these types of individuals could actually go and again make the pandemic worse. So then the eighth compartment is the number of recovered individuals, but who are permanently disabled and are likely not very mobile, and their ability to get, even if they do get reinfected, the chances that they'll go around spreading disease would be limited because they're quite disabled by that. So then the ninth compartment would be individuals who have recovered but are not disabled. So as a result, if they do get reinfected, they could actually spread the disease. And lastly, of course, and sadly, individuals who have actually succumbed to the disease. Okay, so let me describe to you this flow chart that basically pictorially explains the nature of. You see, there are various compartments here that are listed. S corresponds to susceptible, E corresponds to exposed. If you follow the arrow, it tells you what's going on. So, for example, the susceptible compartment S some of them could get exposed to the virus, and so they become so the susceptible individuals can get exposed. So then the exposed individuals can either become symptomatically infected, which is the compartment IS. So there's an arrow that connects E to IS, and E2, the exposed individuals can either become symptomatically infected or asymptomatically infected. So, so like that, you'll see that there are lots of arrows and lots of compartments, and they'll tell you how all these compartments are connected in our equations. So these are the equations, the compartmental equations that we have to solve. So you see that ds by dt represents the rate of increase of the number of susceptible individuals, and d by dt of E represents the rate of increase of exposed individuals, and so on. So these rates will involve various other compartments and certain constants called alpha and mu. So these alpha, mu, and so on, these constants have to be fitted by comparing with actual data in the field. And then once these numbers are fixed, then these equations acquire predictive power, and they tell you what will happen much later after the initial conditions have been used to fix these constants. Okay, so in this slide, I'm going to describe the effect of lockdown. So there are three types of lockdown. One is called the continuous lockdown, which involves locking down without a break. And there's a periodic lockdown, which involves relaxing the lockdown after a couple of days. So for example, you can lock down for 7 days, then relax for 5, and again lock down for 7 days and so on. And the third type of lockdown is called the light switch lockdown, which involves locking down when the number of cases crosses a threshold value. So we'll see that this light switch lockdown is quite effective in mitigating the peak or reducing the peak of this disease. So in this slide, I described the effect of periodic lockdown. So the first plot, the blue plot, tells you what happens if you 7 days and relax for 5 days and then again lock down 7 days indefinitely. So what will happen is basically it buys you time. So the peak of the epidemic shifts towards a later time when it gives you time to ramp up your medical infrastructure. So the really effective type of lockdown is what's called a light switch lockdown, which involves locking down when the number of infected cases crosses a certain threshold. So if you lower that threshold, you will see that able to quickly bring down the peak, as you can see in the second plot. So in these plots, we see the real importance of quarantining and testing asymptomatic individuals. So in the top left plot, you see that if you don't test at all, the peak is very high. But then, so that corresponds to the tau q parameter being infinity. So then if you test, so the moment you decide to test, you will see that you're doing yourself an enormous service because the peak comes down dramatically. So even when the TQ is as high as 600, so the peak has already dropped considerably. So this tells you that testing plays a very important role in mitigating this epidemic. So that's true for various other types of testing and quarantining procedures that these plots describe. So they all share a similar feature. So if you don't test, the peak is very high, but if you test, the peak dramatically drops and so on. So in this table, we describe the values of the constants that we use. So remember that in our compartmental equation, there are a whole bunch of constants whose values had to be fixed by comparing with observations. So this is what most of are obtained from. We had to adjust them so that the results of our compartmental models matched with the initial observations in the field. So in this plot, you see the comparison between the actual data we obtained from, for example, the Worldometer website and the results of our model. So we adjusted those constants in that table until we were able to reach a sufficiently good agreement. So once this agreement is seen, say from March 12th up to April 23rd, so this model has some sort of predictive power. So it will tell you what will happen, say several months down the line. So that's the reason why this activity is important. Modeling is important because it has predictive power over a time scale of, say, months. Okay, concluding remarks, what are the inferences that we could draw based upon our efforts? So the first one is the lifting of lockdown could have serious repercussions in terms of the size of the infected population and the number of deaths. So that it could be in the tens of crores if you lift the lockdown without widespread testing and quarantining individuals. So I told you that lockdown simply buys you time. So just locking down is not going to kill the disease. So even locking down for a year would not be enough. And lockdown, so if you lock down around 2 years, then of course the disease will die on its own, but at an enormous social cost of deaths. So of course the deaths would be in the tens of crores if you don't lock down, but if you lock down for a full 2 years, you still have a huge number of deaths. So in both these cases, I'm assuming that we completely forego testing and or nearly forego testing and quarantining. So if you forego testing and quarantining, you either lock down for a full 2 years and suffer 30, 39 or 40 lakhs of dead people, or you do something even worse, which is you just let everybody be as they were normally, and then you suffer a death of around 15 crores. So that's the whole point. So then you really have to test and isolate infected individuals before you lift lockdown. Okay, so the time has come to wind up. So I thank all of you for listening, and we especially our team of Ashish Menon, Nitin Rajendran, Anish Chandrachud, thank all the organizers and everyone involved. We hope to beat this pandemic, and thank you.
Thanks, Girish. Maybe in the interest of time, we move on to the next talk because we are running out of time. So I suggest that we have back-to-back talks by Rajesh Sundarasan and Harshal Hatnagarkar. After that, we'll get back to questions. So Rajesh, if you are ready, we can start.
Yes, I'm ready.
So
Can you hear me?
So we now move to a new class of, yeah, we can hear you. We now move to a new class of models, these agent-based models, and Rajesh will be talking about unlocking the lockdown in India. So Rajesh, you start whenever you ready.
Are you able to see my screen?
Yeah.
Okay. So my name is Rajesh Sundarasan. I'm from the Indian Institute of Science, and this particular work is joint work with TIFR with technical support from SAP. So I'll quickly begin with some acknowledgements. So this is my team from IISc, Nitin, Nihesh, Preetham, Sharat, Narendra, and Aditya Krishnaswamy. From TIFR, Sandeep, Ramprasad, Piyush, Prahlad, Subhada Agarwal, Siddharth, Anirban, and Anand. And we've been closely working with the Karnataka State Disaster Management Authority, Manoj Rajan and his team, SAP Rahul Lode, and many colleagues from various institutes. So here's a quick introduction. So the lockdown has been upon us since 25th March 2020. Must emerge out of this. And we need tools to evaluate strategies, various strategies of emergence. We also need tools to evaluate, to adapt to circumstances. So we have come up with two tools. These are different categories of tools from the ones that you've seen, which involve SEIR modeling. This one is an agent-based city-scale simulator. We have made it open source. I'll also do a quick demo of it, or at least show some snapshots. You can go to this webpage, cni.iasc.ac.in/simulator, and you should be able to play with it yourself. We also have a workplace readiness calculator as a means to adapt to circumstances and to enable city administrators to make various decisions. This too can be experimented with the same site with workplace-readiness. From the outset, we were very clear that we want this to be a tool to be used by city and state administrators. Our interest was not to write papers on this. We wanted tools to come up with tools that these people could use to evaluate unlockdown strategies. So we have already conducted various studies, various phased emergences. That's reported in our report of 19th April. Just Google search for unlocking the lockdown in India, IISc, TIFR, and you should be able to get to this report. We have also done another report on the importance of compliance. We have done one more on the impact of train services in Mumbai. These are things that we are writing up at this moment. Also, there is another study related to what type of containment zones are most effective, ward-wise or 100-meter radius zone-wise containment. This is also something which is forthcoming, and workplace readiness reporting and a strategy for opening up more offices. So I'll say a few words about this at the end. So what is our simulator? It's actually an agent-based simulator. We have taken 2 cities as example cities. One is Bangalore with 198 wards, and another one is Mumbai with 24 wards. Both have 1.23 or 1.24 crore agents. The map that you see has the population density color-coded. So what we do is we basically get population information, census data, and geographic information, neighborhood wards and things like that. What are the wards, what are the ward boundaries, etc. And then we curate this data and come up with a map that essentially tells us where are the individuals, how are they associated with other individuals, and so on. I'll come to that in a minute. And then what we do is create a synthetic city out of this. Once the city is created, we basically look to the biology of this particular disease, get parameters related to the evolution within a particular individual, and then seed the city with infections and see how the infection spreads. Now, the city that we built has various networks, individuals and networks. There is the home network. There is the there is the home network that you see here. I hope you can see my pointer. There's a school network. People of school-going age go to schools. There are grocery shoppings and other such things, which is the community network. You might go to work, that's factory. You might go to a hospital. You might go to offices, and these are all interaction spaces. And we basically build a social contact network based on these. We also have a transportation network. And then once we build this, once infection is seeded, let's say a particular person is infected. This person belongs to this location, which is, say, a public place. And she might spread this disease to another person. That person goes to, let's say, his home, his office. He might spread it to somebody in his office, and that person may go to her home and spread it to somebody in the home. So it's really a bunch of interacting networks, and we model all of this, and we are faithful to the city. So how is this different from the SEIR models? The interactions are based on home network, school network, office network, community space network, transport space network. So it's not a homogeneous network as is usually the case in SEIR models. In compartmentalized SEIR models, these are relaxed to some extent. But here we basically take the actual network into account. It also takes into account in building these networks, the demographic and the transportation related details of the city. Why do we do this? It enables targeted study of interventions, phased opening of some industries, transport, etc. And I'll describe some study outcomes. So how faithful is our city to the true city? So in blue, you will actually see the data from the city. And in red, you will see what our synthetic city has. So if I may request others to mute their microphones, that would help. So are you able to hear me?
Yes, we can hear you loud and clear, Rajesh.
Thank you, Jasdeep. Yeah. So the blue one is essentially from the city parameters, census data, and so on. The first one is basically age distribution, and we match when we instantiate individuals. We try to match this. The next one is household size. We match that as well. How many households are there with just one person? How many with two, and so on. This one is a workplace size distribution. We try to match that. And you can see that towards the end, our matching is a little off. Those are the very large ones. And here you would see commute distances. So the blue one is our model. which is taken from the city data. From our transportation department gave this information to us, ward-wise origin destination matrices, and that from that we came up with this model and made our simulator match this. And the last one here is the school size distribution. So our synthetic city basically has this level of fidelity with the actual data. Once we have this, we can essentially encode one more set of things, which is the infection progression within an individual. I'll not spend too much time on this, but once an individual is exposed, he or she passes through this incubation period, and a pre-symptomatic or an asymptomatic period, symptomatic period. And then if the individual doesn't recover, there are other stages: hospitalization, critical, deceased, and so on. So we study several symptomatic fractions, 0.6, for example, or in this case, it is 0.33. So our studies involve various parameterizations. Now I'll give some outputs from our mini city simulator. And the mini city simulator has these parameters that you can input. So you can choose which city you want, Bangalore or Mumbai, if you go to that website. And then you can also provide various parameters. These are the disease progression parameters and the transmission coefficients. After this come the various interventions that we have programmed. Some of these are essentially hard-coded, but our full-scale simulator is more amenable to other kinds of interventions. Here you can try only the ones that are given here. Once you do this, you can essentially launch the simulation. This is for a smaller scale city of 1 lakh, and you'll see the number symptomatic, number infectious, and so on. And you can also track where the infections came from, and so on. So this is the outcome when you have no intervention. This is sort of the outcome that happens when you have an intervention, which is a lockdown, and this lockdown goes on for a long period of time. So you will see that in this particular small mini city, the infection has capped at 6,000 for our model, whereas without intervention, it's much larger. Now, you can also try out something here, which is 40 days of lockdown followed by 30 days of home quarantine, etc. There are many things that are here. If you choose this, you can see that lockdown has had its effect. And then there is 30 days of home quarantine, which basically, so the initial phase is actually no intervention for about 25 days. The simulation begins on March 1st. Then lockdown kicks in and then brings things down. But then once you ease the lockdown, there's 30 days of only home quarantine, school college closures and other things, then things start to go up, but somewhat slowly. And then after that, you essentially see things picking up again. So one can see these kinds of behavior in the simulator. That this is largely for educational purposes, for people to play with these interventions and understand the importance of compliance and so on. So for example, you can change the compliance factor here, which is essentially how many households comply with the particular directive that has come, or the particular intervention, and you will see the outcome change as a consequence of varying compliance probabilities. Now, there are many parameters. Much of it is actually related to matching to the city. This is all city census data, household distribution, etc. There are many disease parameters which are based on papers that we have looked at, and we try out various parameters. The other thing which we use in our which we tune or calibrate are these contact rates. And there is a home contact rate, school contact rate, office contact rate, and so on. There's also a seed number and a seed date. These are the only parameters that we tune. All others are essentially just taken from the city data. Of course, there are many other things here which so for matching to the marginal distributions, you can have certain parameters put in there. So those we are choosing in a somewhat judicious way. And we calibrate, we choose these parameters by calibrating to the time series of the first 200 deaths in India, assuming that all of them happen in this particular city. And then we let our city scale simulator run on our city. So I'm now going to describe the output of various studies that we have done. So maybe 2 or 3, depending on how much time I have. So this first study is something which we have highlighted in our report of 19th of April. At that time, the lockdown date was potentially 26 days, and then we evaluated a phased emergence out of this. And the phased emergences involved various kinds of emergence. For example, this one just comes out with only case isolation, lockdown restrictions end, with case isolation and home quarantining are active. But then once the lockdown, once after 20th of April, pretty much other things are inactive. There is then school closures. And then here we studied an odd even kind of strategy where 50% of the office going people could go to work. I'll come back to elaborating many of these things. So this is just to highlight the kind of outcomes that we have. So for example, on Mumbai, we tuned our parameter tuning was only to the India deaths up to April 10th. But then we were able to see, and that too in the no intervention scenario, but we were able to see this bend, or we were able to predict this bend at that time. And we see that our simulator is essentially capable of predicting the fatalities reasonably well. So we were very happy because to capture this, because this is something that we had not put in our simulator, but somehow we were able to match to this. This is the number of hospital beds that we are able to predict based on our disease progression. I'll not spend too much time on this. So that's the outcome. We did this study for both Bangalore and for Mumbai. I've presented here only the Mumbai results, and that too for an asymptomatic fraction of 0.33. We have a similar outcome for an asymptomatic fraction of 0.6 as well. Our second study involved was a study to highlight the importance of compliance. So let me elaborate on this a little. So the Ministry of Home Affairs order of 15th of April said that many restrictions will continue until the 3rd of May, but a few activities may be permitted from the 20th of May up to 3rd of May. And these were left to the local city and state administrations. For example, the city and state administrations could enable IT and IT-enabled services, but they could operate at 50% strength during this period between 20th April and 3rd May. Government of India and state and union territory offices could function at 33% attendance, but there are some critical offices which could operate at full strength. Manufacturing and other industrial establishments with access control in SEZs, for example, they could operate provided that they follow some standard operating procedures. So what is the impact of opening up of each of these things? So this is something that is difficult to study using an SEAR model unless you bring in these compartments. It is rather natural to study these in our agent-based model, and we have done that. Another parameter that we brought in is that compliance may be an important factor. There isn't sufficient data to assess precisely the degree of compliance to the government orders. But Google data, for example, suggests these kinds of movement reductions. There is some compliance, but it's only to some degree. So we explored two compliance scenarios, 70% of the households comply and 90% of the households comply. And I want to share a comparison of these two with opening up of some offices. So how do we open up the offices? We thought of these phased emergences. So no intervention from the 1st to 13th March. In Bengaluru as well as in Mumbai, there was some sort of a pre-lockdown between 14th or 16th, depending on whether it was Bengaluru and Mumbai, until the 24th. And then from the 25th onwards, 25th March onwards, there was the national lockdown. That lockdown went on until 23rd. And then there could be some openings that were possible based on the state authorities' decisions. And in Bangalore, some offices were actually open. Now, we studied various attendances. For example, you'll see that Government of India and Government of Karnataka offices in Bangalore could operate during this period at 33% and then 100. Or alternatively, it could operate at 50% or, this is IT and IT-enabled services. They could operate at 50% or not at all. And then 50% during this period between 4th and 31st May. And then between 1st and 4th July at 100%, and so on. Schools and colleges were closed. They could possibly open on the 1st of June. So we evaluated these scenarios, and there are some definitions here. Let me quickly go to the outcomes. So this is just to indicate that in Bangalore, the compliant, this is the fatal number of hospitalized cases. This is our lockdown 70% prediction. This is our lockdown 90% compliance prediction. So we seem to be closer to the 70% in Bangalore. And this is what we have with workplace control. So you could open all the three or close all the three. By all the three, I mean these three: Government of India, Government of Karnataka, IT and IT-enabled services, and SEZs. You could keep all of them closed or all of them open. They would be here with 90% compliance. But with 70% compliance, they would be here. What this suggests is that perhaps you could open up and ensure compliance, and things may be at a better level than operating at 70% compliance with lockdown fatigue. So that's one takeaway from this particular study. So here are the same estimates, but in linear scale. So this is a 70% compliance, and this is the 90% compliance. 90% with opening of workplaces may actually be better than lockdown with 70% compliance. The figure on the right is the same fatalities in log scale. I would now like to point out another study, which is essentially the city scale simulation study for Mumbai to understand the effect of trains as well as phased emergence. So I'll be very quick on this because I want to spend a couple of minutes on one other new study. So here what we modeled is after, let's say, a certain date, we are going to have case isolation, home quarantine, testing, etc. But masks became more prevalent starting from April 9th onwards, face masks. And then we wanted to study containment zone, soft containment zones. And that is something that I will show the outcome of various kinds of containments. And then we also said that 60-year-olds and beyond should practice social distancing. Now, the containment strategy was that the ward is completely open when the number of hospitalized cases in that ward is 0. When it comes to about 0.1% of the ward population, the number of hospitalized cases, we close the ward to about 0.1% of, so the leakage of about 10%. So this is to model essential services being provided to that particular ward, which has been cordoned off. And in between, we basically go in a linear way. This is something that we can easily tune in our simulator. The amount of ward closure is proportional in between to the number of hospitalized cases. And this is what we see. So we also looked at similar phased emergences out of the lockdown, and we saw the following. So for example, there are solid curves and dashed curves here. The solid curves correspond to trains being off, and the dashed curves correspond to trains being on. Focus on the red curve. So this is when the trains are off, and this is when the trains are on. And the red curve is when you have opening up of all the industries that I had mentioned in the previous slide. Now, when that happens with trains off, this is what you see. This is the number of simulated hospital beds that we need. On the other hand, if you have the trains on, the spread increases. So there is a model that we have for what kind of interactions happen in the train, and we have a logic for this that we will we'll put up soon. But then this is the kind of prediction that we have. So one can also see, for example, the doubling time, how it actually increases with the lockdown. But then when you open things up, the doubling time comes down. And then when you close things, this is due to the ward closures, the doubling time goes up again and so on. So there are these huge swings that are negatively correlated with the disease spread. So when this is high, then the wards get closed and you essentially have smaller doubling times. And the dotted and the solid and the dash correspond to, this corresponds to trains off and this corresponds to trains on. In any case, we have this particular study as well, and a report is forthcoming. There's another study that we did, which is related to what kind of
Rajesh, 20 minutes is up, time. So just quickly.
Yeah. So
no, you quickly finish.
Yeah. Okay. So then I'll skip that previous study, and then I want to then highlight in maybe just a minute or so another way to emerge from this lockdown, which kind of throws. Which trusts users and empowers users to make responsible decisions. And I want to highlight quickly this. So here's the motivation for this. So lockdown is essentially a top-down straitjacket approach. It treats all activities as equally risky. But then certain activities could be carried on if people take precautions. And the person that's making these decisions about lockdown is unclear as to what activities these are. That information is available with the individual agents. The individual agents, on the other hand, don't have a perspective of the overall spread of the disease in the system and how their decisions might impact the broader disease spread. So this information asymmetry is a problem. So why not use some ideas from economics and come up with the soft touch approach? So the soft touch approach could be that the social planner advertises a readiness threshold. If your particular firm is ready, is COVID ready, and your readiness threshold is met, you cross this readiness threshold, then you can operate. Otherwise, you cannot, or otherwise you can take decisions to meet this readiness threshold on your own. Agents then decide, once this readiness threshold is advertised, the right mix for them based on their firm's objectives. We think that this is likely to have greater acceptance. It's also adaptive, because if the disease is, if the epidemic is spreading in a somewhat alarming way, then you can increase the readiness threshold. If things are going well, then you can decrease the readiness threshold and allow more activity. So just quickly, here is a particular readiness threshold calculator that we have. So you can tell what kind of establishment yours is, whether it's an IT or IT software park and so on. You can also provide other details about your infrastructure, office infrastructure, the number of employees, epidemic related precautions you have taken, and so on. And then you can, there are many such things. How many people travel, what distances, what kind of, how many toilets do you have, how often do you clean them, what's your cafeteria, pantry, kitchen parameters, what kind of interactions do people have in your offices, and so on. And then if you hit the submit button, you will essentially get a readiness threshold. So this is actually a readiness threshold calculation for the office that we sit in. So we have a readiness threshold of 751. We are very poor in cafeteria. Let me make this bigger. We are very poor in cafeteria, for example. So if we take some actions here, perhaps we'll meet the threshold and we might be able to operate. And the important point here is that you get some suggestions here, which are concrete steps that the entity can take to increase their readiness threshold. So I'll go back to my presentation and maybe end with this. There are some weighted averages of the measures taken, which come up with the score in some cases. For certain other things, employee interactions, etc., we basically look at what would be the contacts for the parameters that people have input. And then we estimate the doubling time of a hypothetical infection. And if it is smaller than some number, then if the doubling time is larger, then we basically say that this particular firm is ready as far as that interaction space is concerned. Thank you.
Thank you, Rajesh. So we move on to the last talk, and then we can go back to questions. So the last talk is by Harshal Hayat-Nagarkar, and he will be also talking about another agent-based model. So Harshal, if you're ready, we can start.
Yes, just sharing my screen.
Yeah.
Can you see my screen?
Yes, we can see.
Yeah, thank you. Thank you, Rajesh, for a wonderful presentation and other presentations also. And this is the work that at ThoughtWorks we are doing. This is in collaboration with Dr. Gautam Menon of Ashoka University. And we are sharing early results from a large-scale agent-based simulation for a greater Mumbai metropolitan region. So we, just to give you a very quick primer, I think Rajesh has already covered, but we see there are three layers of agent-based simulations. The bottommost is the spatial data, building schools, shops, offices, etc. On top of that, you have environmental factors, and then you have people moving, making decisions, living their daily life. And there are three ways of modeling, from minimalist to realistic, and then there could be intermediate models also. So if somebody were to simulate war strategies and use them for learning, training, and other decision-making purposes, you can see chess can be used as a war strategy simulation, a minimalist one, and then real-time strategy games can be used where there is more dynamics And finally, you can have actual military war games. And all three are simulation. One simulation type or many simulation types could be useful depending upon the purpose of any individual. So here, the work that I'm going to present is based upon a simulation framework we built. We call it Rust. It's an epidemic simulation framework developed in Rust programming language. It's open source. We open sourced it sometime in mid to late March. It is distributed. You can simulate one or more cities with that. It follows the minimalist approach, something like the chess I mentioned, with representative functionality. And the disease dynamics is the Mordecai SCR model that we already discussed. And here in this simulation, the clock tick is equal to 1 hour. So in case of agent-based simulation, you need to maintain your own clock as the agents are making, they are moving, on the grid or on the geography. And usually we simulate up to 10,000 ticks or 10,000 hours, which is a little more than a year. So we have different agent attributes. We have working, non-working population. Mobility-wise, people using public or private transport. We have 3 different types of works: healthcare workers, essential services worker, as well as others. And we have modeled age and gender, but we have not used as of now. Agents follow 24-hour daily routine, wake up in the morning, do household activities, take public or private transport, go to work, work there for 8 hours, and then come back using the transport of choice, and then finally do household activities, sleep for 8 hours to wake up next day. And we also have support for a synthetic population that is still work in progress, actually. In addition to that, our city is a grid-based geography. We have different areas demarcated as residential, where people live, then workplaces, transportation, which is actually public transport, and hospitals. And we have modeled 3 interventions: quarantine in hospitals, city lockdown, and mass vaccination. And mass vaccination is because we started work on Rust last year, actually. So at that time, there was, we all had assumption that the vaccines could generally be available for disease spreads such as influenza and so on. And in addition to that, we have a transport matrix for intercity transportation. This is not a commute, where it is not like people start in the morning, go to the office, and then come back in the evening. This is travel, where they move to a different city, and they may stay there for definitely more than 1 day. And the schedule is 24 hours. It's a unimodal, so we are not differentiating between different modes, such as rail, road, or air. And then lockdown intervention, we have 0 movements in the lockdown, except that essential services are permitted, along with some movement of healthcare personnel. In addition to that, we also take into account leakage as in people who are moving across, but they do not belong to either of these 2 services, and which could mean that they could be source of infection. So this is generally the minimalist approach, like I was mentioning, of a typical city. You have the housing area, which is in light yellow color, and all the blue dots on them, these are the people staying there. And then there is a pink area, which is work and transport area, which is light orange, and then hospital area, which is light blue, and then other area, which can be used for hospital expansion and other things, other purposes perhaps. There are some other usages we have in mind that I will discuss towards the end of this presentation. This is the Mordecai SCR model that already Gautam discussed, and we are following the same one. No change there. So to simulate COVID-19 spread over the Greater Mumbai metropolitan region, we try to model it, and we have some early results as early as today morning itself. And this is the Greater Mumbai region, and the model setup is such that what we do actually is we try to simulate each and every individual in the city living their life, and then the way each city can have a large number of individuals. Now, because of the computational resources needed to simulate a large city, we have typically seen when a city population is below 5 million, we are able to simulate it pretty nicely. 5 million is where we start seeing some hiccups in terms of execution times and so on. So Mumbai population being much larger than 5 million, what we thought to divide the entire population of Mumbai into ward wise, and each ward can be simulated as a city. And for each ward, we have a relative sizing for the population density, which means the densest, most dense region of the ward of the Mumbai, that will become the size 1. And then as it becomes sparser and sparser, then we create larger and larger grids for that. We tried to simulate a scenario with lockdown only. So we have a transport network that by which the wards can people in different wards, they can move from one part to another part. But the way, because of the communication framework we are using, the commute framework would choke up the distributed messaging framework. So we decided to start with a lockdown scenario. And here in this case, all the wards are under lockdown. Only health and essential services are possible within and across wards. So people can move from one end of the city to or from one ward to another remote ward, and so on. There is leakage which is factored in, people movement across adjacent wards, but not necessarily moving to remote wards. And then there is inter-ward transport network that essentially, like I said, does not represent commute. The healthcare workers stay at hospitals for 2 weeks, and then they come back to their home ward. And lockdown is lifted under a condition that there are 0 cases for 3 weeks continuously. So under these conditions, we tried to simulate a lockdown scenario within Mumbai. And we are also currently, as of now, we are working on scenario without interventions, no hospitalization, people movement within ward, and so on. I think that will take some time for us to get the result. So the input parameters were synthetic population, approximately 12 million agents, 1.2 crore agents we created using ward-wise census data, and then relative grid sizing based on the population density and mobility. For that, like I said, people using only transport for essential and healthcare workers and no commute. And for disease dynamics, the transmission start day, we assumed as it starts on day 5. End of infection for severely infected people is 26. End of infection for mildly infected patients would be 12. And for end of infection for asymptomatic people who do not show any symptom whatsoever is 9. And with other these details, we concluded the disease dynamics. And then we wanted to choose a dates. A date 13th April gave us all the necessary details such as infections per ward, which we seeded, and then that was the setup with which we ran the lockdown scenario. So these are the early results. This is an animated GIF where you can see the infection is spreading slowly, and we have simulated close to 10,000 hours of the simulation. And you can also see some of the regions are becoming greener as well. So based upon this, we thought why not to have a look at some of the recent details that BMC, Brihan Mumbai Municipal Corporation has shared. So there is a report, progress report. So as of 7th of May, we see there are some close to 8,784 active cases here. And from the simulation, we could see that there are 8,116 active cases. The number of recovered are more, in our case, 3,500. There is total recovered here are 2,435. Of course, these are very early results, and we have just started simulating this for the disease dynamics because all other components are in place now. And this is the interactive dashboard that we typically use to slice and dice across various wards, how the data is moving from how the infections are moving from one region to another region, how they are spreading. So in addition to that, myself being a computer scientist, I would like to share some technical discussion. Some of you may, may find it useful. So the current architecture is such that we use, an Apache Kafka, which is the communication backbone, and then each ward has its own engine, what we call as IPREST engine, and these IPREST engine, they need to be synchronized for their own clock, because each ward has to have its own clock. And then there is a vector clock synchronizer that keeps track of how each engine is maintaining the clocks. And typically 24 hours the synchronization happens because of these vector clock synchronizer. In addition to that, the current IPREST code, it uses only single core, but we have implemented it with what is called as mechanical sympathy, such that the code is written by understanding the internals of computer architecture, the underlying processor, and so that we try to keep the loops very, very tight to each other, so that it uses memory locality and so on. We also use some SIMD, data parallel instructions, so that the data structure access and data structure manipulation time can be minimized. And so basically, if somebody may be curious to know why we chose Rust, we had 3 goals. One is performance, the second one is flexibility, and third one is robustness. So via Rust programming language, which came from Mozilla, the Firefox makers, it offers performance comparable to C and C++, but without the overhead of explicit memory management, which typically becomes source of many errors, difficult to find out, difficult to discover and later mitigate. In addition to that, it offers robustness of other well-known languages such as Java and Go, which have the overhead of runtimes, which Rust does not have. And in addition to that, Rust is very flexible because it supports object-oriented and functional paradigm. It also supports fearless concurrency as a design philosophy, which is very important, as you would like to run it on multiple cores and multiple machines. And for example, just to give you a sense of performance, our first implementation of the epidemic model was on Gamma platform, which is very popular for prototyping and so on. And so the dynamics was smallpox dynamics that we had last year, and it took 60 minutes on the 100+ cores of a large server for 10,000 agents, whereas IPREST finishes for 10,000 agents within less than a minute on a single core of a laptop. So till now, highest we could simulate 50 million agents across 10 virtual cities of 5 million each. And we are hoping that we will be able to scale beyond that as well. So IPREST is still work in progress. We are adding lots of features. So household information to form families, for example, in synthetic population. This is something an ongoing work. We are also trying to add shared spaces such as shops and markets. We are trying to incorporate age and comorbidity into the Mordecai model if possible. Various what-if scenarios for imposing and lifting lockdown. That is another work in progress. Then looking at various news reports and trends, we had anticipated earlier as well that reverse migration could become a problem, as it has become. So we would like to model that. In addition to that, we think this is human behavior models is going to be an orthogonal model for many other things, basically, whether it is compliance, as Rajesh spoke, or reverse migration and so on. Commute transportation network, effect of using PPEs and masks for healthcare staff as well as general populace. Herd immunity we are interested in simulating. And finally, so we try to generate a lot of data that can be consumed by an outbreak analytics package and so on. So what do we need in order to achieve this and beyond? We would desire to have a ward level census data across India that would go into synthetic population or synthetic information kind of package. GIS data, including residential roads, offices, hospitals, and so on. Hospital details specifically, such as scheduled beds, how many are available, ICUs, are there any specializations such as ventilators, and so on. Clinical cases details within India and elsewhere, so that we can actually precisely compute the disease dynamics probabilities and other effects using machine learning and other data science techniques. Commute data for synthetic information, again, migration data. And then we all, of course, need community of users who would try IPREST and then give their feedback if they find it useful or not. And if they don't find it useful, even we would like to hear even that from them. And next in the evolution in this line, we are looking at BharatSim. It is the first ultra large scale simulation for entire India. It's a research collaboration with Dr. Gautam, and the scope is much beyond IPREST. The BharatSim will have its own identity, so IPREST and BharatSim will coexist. So when we are seeing pan India scope, it is the complexity of the geography, the population, climates, because each region has its own microclimate and so on. Going beyond epidemiology, it could mean that economic policies and then climate change policies and so on. And unlike IPREST, BharatSim is going to be based on GIS and other related data. So I think what we are trying to share is, based upon the philosophy, all models are wrong, some are useful. So we are trying to help build a framework that can, help researchers to build useful models. And I presented this on behalf of my team, Engineering for Research, where we exclusively collaborate with research organizations. And you're most welcome to write to us, and you're most welcome to try IPREST. Thank you so much.
Thanks a lot, Harshal. So maybe we take a couple of questions for Harshal and Rajesh. So one question was, how realistic are the models in incorporating city information? So heterogeneity in the city landscape in the terms of population density, households, and so on, and also about informal sector and formal sector. So Rajesh, would you like to take that?
Yes. So we take into account the population density in each of the wards. And so households are instantiated based on the census data that we have. So that's it's faithful to that extent. So there was a question from, I think, Atiyab Zafar on whether we take into account apartment complexes and other households. We don't do that. It's not to that level of granularity. But when we know that there are this many number of households in the city, we put them in that particular ward. They are all located in that ward. So a 1 lakh city with an average of 4 people per household means that there are 25,000 households. They are all placed in some way in this ward. Now, what we do take into account is if the particular ward has a very high population density. So there is a population density parameter. This is something that you can tune. Then the contacts there are likely to be at a much higher rate. So you can essentially provide a higher contact rate parameter for that. So in Mumbai, for example, in every ward, Mumbai has only 24 wards, whereas Bangalore has 198 wards. So Mumbai is a lot more larger wards. So what we have done is we have basically divided each ward into a high density zone and a low density zone. So effectively there are 48 wards, and then you can have a high density parameter for the contacts in that particular zone. So did that answer all the questions that you posed, at least for our simulator?
About the formal sector and informal sector.
Yes.
That kind of
So the census data also gives information about how many people are employed. Now this employment data takes into account the formal sector and the informal sector. They have different kind of contacts. The formal contact is there is an office that is there and so on. The informal contact is a little different. It might be some household help, or it might be maybe deliveries of some kind and so on. So we have not taken the informal, we don't have a very refined model of the informal sector. We just view it as this many people are being employed, and then they are instantiated in appropriate offices based on the office size distribution and the data that we have. So that means that we would instantiate more number of offices and think of these informal sector employments as offices of a similar type. That's of course not true, but this is the best that we could do.
Thank you. So Harshal, I'll throw the other question at you. So what about healthcare preparedness in locally? So do you take that into account into the model about infrastructure and doctors, etc.?
Yeah, so we have a hospital, we have model hospital and healthcare workers. the way we have currently modeled is for each ward in Mumbai region, there are designated number of like 2% of healthcare workers, and now for their preparedness, such as PPE and other equipments necessary, that's something which is on our to-do list. We are making some progress towards that.
What about, do you have information about how many hospitals are there in a neighborhood or how many clinics and so on? Does that information go?
No, as of today, the model cannot consume this information, but we are trying to make some progress in that direction.
Okay, so thank you. So maybe we just move on to some panel discussion in the sense of some broader questions that we would like to address. So some of the questions that basically came up during the chat also, and some that we have been grappling with. So all of these models require data. So how much of data is available, and what the modelers feel should be available to make good modeling and also good predictions and so on. And the broader question is how, as a modeling community, how do we contribute to the epidemic mitigation in the country? How realistic are the models? What do we expect from these models? What not to expect? So, for example, people got scared when there were some projections about millions of people dying. Is that realistic? There are a lot of pessimism about this compartmental model. So maybe some people can comment on that. And then there's also the question of whether deterministic models are good enough and should one look at stochastic models. So some words about these models, if some of you can comment. Another question is about herd immunity. So this is a term that is being thrown around quite a lot. And local or global, so should we think about local herd immunity, or should one think about herd immunity on a larger length scale or geographical scale? And do models help us in understanding or achieving this kind of herd immunity or the time scales involved? So maybe some of you, the panelists, can respond to this. So Gautam, would you like to take up some of these questions?
Yeah, just a sec. Let me just share my screen. Can you see my screen, Pinaki?
Yeah.
Okay, at least to the second question that you raised, I mean, that's an important one, because one question that as modelers we are asked a lot of the time is, to what extent are you just playing games with models, and to what extent is what you're doing useful in terms of planning, of national planning, of working on a really tight time scale to be able to actually be meaningful in terms of what you're trying to do. So that's something for us who work as modelers to consider. At what level of what we are doing, is it relevant? And I've also been asked recently about the fact that there are many people, there are many models floating around, let's say at least about 20 or 30 of them that people have different done. Is there one set of models around which the community can coalesce on, in order that government is not faced with the need to look at 20 different models to try and figure out what's the detail, what is the difference between model 1 and 10 or 12 or 13, because it has no one to sort of advise it at this point. So what's on my screen is just a quick run through of different types of models that people have been talking about. So we've seen a whole lot of deterministic epidemiological compartmental models, of which InsiSim is the one that I've been involved in most closely, and I think has the right requisite level of detail to be a fast deterministic thing. It's a sort of point of first entry if you want to ask a quick question about what might work, what might not work. Then there are the agent-based models which come later, which have a whole lot of complexity built into them. And they're complicated, they're hard to write, they require a fair amount of expertise that is not really necessary for someone who's skilled with numerical methods to figure out how to write, how to code up 8 PDs, actually 8 coupled ODEs in a suitable form. It's really there, the epidemiology is important to determining what you want to choose. But there's stuff in the middle that we're not paying enough attention to. And I want to put it out there, we haven't seen any Gillespie-based models, and I think that this is the next frontier for people who work on deterministic compartmental models to think about. And this, I think, should be the next direction for people who are working with the InsiSim initiative to think about. That now that a large chunk of that work is already over, we should be moving into seeing how we can make that put stochasticity in. And the advantage with Gillespie-based models is, exactly as Mukund pointed out, the nature of the progression of the disease is more complex than the simple exponential time scale that an automatic simple rate equation approach gives you. You can put in the levels of the disease and a better description of the disease at that point. You can also put in complex network structures in terms of social interaction. You don't quite have the geographic way that agent-based models are able to deal with it, the underlying geographic information that you can do with agents and where people stay, where people work, etc. But this might be somewhere in between where there is a gap and where one should work. The other point that I really want to emphasize is statistical models and data analysis. We have essentially not very statistical approaches that are deep and targeted to the sort of problem that we have. There's huge amounts of potentially underreporting, bad data coming out of government, stuff. People don't seem to trust the government numbers anymore. They seem to be looking more at the aggregated information that people seem to be picking up from newspaper reports, from state reports, etc., etc., etc. So can we develop better statistical methods? So we need more epidemiologists, statisticians, health economists, sociologists. This group is largely a group of physicists, applied mathematicians, engineers, computer scientists. But at some point, we have reached a stage where the input that we need must come from outside these fields. That's again a point that I wanted to raise, but particularly to stress the need to come behind one set of models of each type, a deterministic model, a stochastic model, and an agent-based model that can function at different scales with different people involved in them. And we can say that, look, this is the one that we trust as a community to be able to be helpful in predicting the future course of the disease. Yeah, sorry, that's all I had to say.
Could I add something to that? This is Mukund.
Yeah, sure. I was going to ask you. So carry on.
So in addition to, of course, I agree with every point that Gautam just mentioned, and it's very carefully thought through. So I can't emphasize how much I agree with what was just said. So I have one other piece to add. So I think I think we can all agree that it's not the models that are going to save us in the end. It's what happens on the ground. It's the people in the hospitals. It's the biology of vaccines and so on and so forth. And if that's the case, then what is the role of the model? And Gautam emphasized the predictive role. I think the complementary role models serve are explanatory roles. They look back and tell us what we have been through and tell us which ingredients of the real world are relevant and which ones are marginal and which ones are irrelevant. And that type of looking back post facto explanatory power is then used and integrated into other ways of thinking going forward, right? So if a model is so complicated that you can't even understand the model, then I think it serves no purpose. So what we should do with the model is try and understand why they are doing what they are doing.
Okay, thanks Mukund for your thoughts. Anybody else wants to pitch in from among the panelists?
So I want to add to the last point of what is present in the model is also probably present in the thought. So on one end we said what will happen on the ground, but question is whether it be policymaker or modelers, are migrant workers present in our mind space? Is hand wash, whatever our recommendation are for physical distancing or hand washing, or this whole concept of lockdown, how long, when we say, oh, 2-year lockdown, even to utter that phrase 2-year lockdown, what does it mean to the lives of the people? Or even forget 2-year, even 2-month lockdown, which all of us have been doing. But what does it mean? What does it do to the people? So in that sense, the importance of a model is also in what all it does not talk about and what all it talks about. And I think that aspect is what, and also, there's no easy answer. I'm just raising question. I also don't have an answer, but that we must be aware of that and we must emphasize that. And that our model suggests lockdown as an intervention, because if that's all our models can do, and of course there are a lot of models here which do a lot of different things. But I'm just saying that the solutions suggested should be very clear, that there are a lot of, the disclaimer should come in the beginning, not at the end, that there are a lot of things that can be done, that are important to be done, but our models can't do it. And therefore that list of things suggested is necessarily not just incomplete, it can be dangerously incomplete at times. So that, and some of the things I mentioned earlier, how to take care of that. So at a very broad level, rural-urban divide, and also within the cities and the elite and the common man, or which in a city like Bombay can be very stark, or in most of our cities. So how do we model that? And when we give suggestion, especially or anything, what does it mean for people in Dharavi or in Mumbai to do certain things, or what should policymaker do or administrator do So there was the issue of homogeneity and heterogeneity came, but I think at least there are just two binaries, rural, urban, where the rural behavior may be very different, the pollution level is different, population density is different, the contact matrix is different. So the rural-urban divide, I think, should be paid more, and within city, then so the urban poor and rural poor, their response and risk both may be dramatically different, which is something that's currently present from our thoughts.
This is Anup Krishnan here. Can I add a few points to this?
Sure. Anup, carry on.
Yeah, hi, I'm Anup Krishnan from IIT Delhi. So I completely agree with the points that have been, that was discussed by Professor Gautam Menon, Mukund Tattai, Om Damani. From my perspective, let me give you a slightly different perspective on this. I am a civil engineer. Okay? So my only connection to biology is that my wife did a PhD in neuroscience. That's my only connection to biology. But what happened is that when this COVID happened, somebody came to me and said, is there anything that you think you can do? Because ultimately, these are some differential equations and people work on differential equations. You work on differential equations. And we do it on a daily basis. So that's how we started this work. And when we started this, I echo with Professor Rajesh Sundaresan that we did not start this work with the aim of getting 3 papers out of it or producing some papers out of it. That was never the aim. Can we do something which is going to help people disseminate the information better and give some indicative suggestions as to this is what is going to happen. This was our intention. And now after going through the symposium, I see that most of the people have ventured into this with the same intention. And I think as a community, one thing that is actionable, I would like to add that I don't think we will have ever an agreement on what is the right model or is there a single model that's going to predict everything. I don't think we will have an agreement on that because everybody will have their own pet model and they'll keep continuing to work with that model. And I think that's fine because that's how science works. We all have our own ideas and we try to develop that idea further and time will, the test of time will tell us which is the best model. But I think a more important thing is that it has essentially created a body of knowledge that different people are thinking and different thoughts have come in this direction. And I think as a community, we should think beyond COVID. I mean, COVID is one thing that initiated this. And I think that's a very good initiative that we have come together at COVID. But I think the implications of this work is much beyond COVID. And it can be applied to many other infectious diseases. So I think one of the major things as a community that we can do is combine the knowledge that we have documented and make it accessible to everybody. For example, I see that most of the people, many of them have made their code open source. Even we have made our code open source. Everybody can go to our paper and click on the GitHub link. You will get the link to all the codes. And we are sharing it on a web page also. We made the web page just with the intention that everybody will be able to kind of access this information, which is otherwise not easy because getting an R0 value is not easy from a perspective of a common person. This was the whole idea of doing this. So towards an actionable outcome, can we think of something like that wherein all the knowledge is put together in different compartments? One is data. Make the data available because I think a lot of us have a lot of data that's combined because the models are using a lot of testing data, a lot of incidence data. We have a lot of district-wise data and even testing data. So can we come up with 2-3 points like this? For example, all the models will be made available. Everybody can test it. All the data will be made available. Everybody can test it. And then probably people who are already working in this area and who want to take it forward, can they suggest how to extend this to other infectious diseases like maybe malaria? Malaria is a big issue in India and many other such diseases because we are going to have now many more cases that are going to happen with. This is just my thought from my side. That's so. Thank you.
Okay, I have a point to make.
Anup, because we now.
Yeah. Sorry,
Anup, we are just running out of time. We just will be kicked out basically by Zoom.
Right. Yeah, thank you.
This is Rajesh Sundaresan. Can I make a couple of
points?
Rajesh,
so you have 1 minute, because at 16:30 we are going, 6:30 will be kicked off.
Okay.
So we have a hard limit.
Yeah, I think we have done quite a bit of epidemiological modeling and some statistics and data analysis. It's time to bring the economists and the sociologists. So I echo the point that Gautam Menon made. I also think that we must come up with more ingenious strategies and think about empowering people to make responsible decisions, and perhaps come up with methodologies by which we can have more activity go on and still manage the lockdown, but or manage the reduction in contacts. And I think lockdown is not the way, but perhaps greater awareness, education, and also actions that people could take. So if we could bring in sociologists in at this moment, it would be very helpful in our studies. Thank you.
So thanks, Rajesh. In fact, ISRC's entire effort is to bring in people from different fields, and we are continuing to do this effort to bring in people from different, we are all coming from mathematical backgrounds in the sciences, but also in social sciences, we would like to interact, and this process is continuing. So one thing I would just like to mention before finishing, that we plan to have a series of these kind of panel discussions based on the topic of modeling and data analysis and so on. So we want to have another one soon, maybe in a week's time. So we'll let you know. Also, if you get to know about modeling efforts, please bring it to our notice so that we can invite the people, so that there are more thoughts and ideas to be shared. And also, we would like to have a white paper or a summary document at the end, which sort of summarizes what are the different efforts that are going on in different groups and so on, so that there is a coherent bed of knowledge that Anup was mentioning that people can act upon and so on. So we have to end now because we are really run out of time. So thanks to Jasjeet and the team at ISR Mohali for helping us to host this meeting, and we hope to see you soon in the next edition of this symposium. So thanks a lot for joining. Thank you.
Thank you.
Thank you.
Bye.
Thank you. Bye.
Thank you.
Thank you so much.
Thank you.